Part 4, String Theory and the Fabric of Spacetime. Chapter 10, Quantum Geometry. In the course of about a decade, Einstein single-handedly overthrew the centuries-old Newtonian framework and gave the world a radically new and demonstrably deeper understanding of gravity. It does not take much to get experts and non-experts alike to gush over the sheer brilliance and monumental originality of Einstein's accomplishment in fashioning general relativity. Nevertheless, we should not lose sight of the favorable historical circumstances that strongly contributed to Einstein's success. Foremost among these are the 19th-century mathematical insights of Georg Bernhard Riemann that firmly established the geometrical apparatus for describing curved spaces of arbitrary dimension. In his famous 1854 inaugural lecture at the University of Göttingen, Riemann broke the chains of flat space Euclidean thought and paved the way for a democratic mathematical treatment of geometry on all varieties of curved surfaces. It is Riemann's insights that provide the mathematics for quantitatively analyzing warped spaces, such as those illustrated in figures 3.4 and 3.6. Einstein's genius lay in recognizing that this body of mathematics was tailor-made for implementing his new view of the gravitational force. He boldly declared that the mathematics of Riemann's geometry aligns perfectly with the physics of gravity. But now, almost a century after Einstein's tour de force, string theory gives us a quantum mechanical description of gravity that, by necessity, modifies general relativity when the distances involved become as short as the Planck length. Since Riemannian geometry is the mathematical core of general relativity, this means that it, too, must be modified in order to reflect faithfully the new short-distance physics of string theory. Whereas general relativity asserts that the curved properties of the universe are described by Riemannian geometry, string theory asserts that this is true only if we examine the fabric of the universe on large enough scales. On scales as small as the Planck length, a new kind of geometry must emerge, one that aligns with the new physics of string theory. This new geometrical framework is called quantum geometry. Unlike the case of Riemannian geometry, there is no ready-made geometrical opus sitting on some mathematician's shelf that string theorists can adopt and put in the service of quantum geometry. Instead, physicists and mathematicians are now vigorously studying string theory and, little by little, piecing together a new branch of physics and mathematics. Although the full story has yet to be written, these investigations have already uncovered many new geometrical properties of spacetime entailed by string theory, properties that would almost certainly have thrilled even Einstein. The heart of Riemannian geometry. If you jump on a trampoline, the weight of your body causes it to warp by stretching its elastic fibers. This stretching is most severe right under your body and becomes less noticeable toward the trampoline's edge. You can see this clearly if a familiar image, such as the Mona Lisa, is painted on the trampoline. When the trampoline is not supporting any weight, the Mona Lisa looks normal. But when you stand on the trampoline, the image of the Mona Lisa becomes distorted, especially the part directly under your body, as illustrated in Figure 10.1. This example cuts to the heart of Riemann's mathematical framework for describing warped shapes. Riemann, building on earlier insights of the mathematicians Carl Friedrich Gauss, Nikolai Lobachevsky, Janos Bolyai, and others, showed that a careful analysis of the distances between all locations on or in an object provides a means of quantifying the extent of its curvature. Roughly speaking, the greater the non-uniform stretching, the greater the deviation from the distance relations on a flat shape, the greater the curvature of the object. For example, the trampoline is most significantly stretched right under your body, and therefore the distance relations between points in this area are most severely distorted. This region of the trampoline, therefore, has the largest amount of curvature, in line with what you expect, since this is where the Mona Lisa suffers the greatest distortion, yielding the hint of a grimace at the corner of her customary, enigmatic smile. Einstein adopted Riemann's mathematical discoveries by giving them a precise physical interpretation. He showed, as we discussed in Chapter 3, that the curvature of spacetime embodies the gravitational force. But let's now think about this interpretation a little more closely. Mathematically, the curvature of spacetime, like the curvature of the trampoline, reflects the distorted distance relations between its points. Physically, the gravitational force felt by an object is a direct reflection of this distortion. In fact, by making the object smaller and smaller, the physics and the mathematics align ever more precisely as we get closer and closer to physically realizing the abstract mathematical concept of a point. But string theory limits how precisely Riemann's geometrical formalism can be realized by the physics of gravity, because there is a limit to how small we can make any object. Once you get down to strings, you can't go any further. The traditional notion of a point particle does not exist in string theory, an essential element in its ability to give us a quantum theory of gravity. This concretely shows us that Riemann's geometrical framework, which relies fundamentally upon distances between points, is modified on microscopic scales by string theory. This observation has a very small effect on ordinary macroscopic applications of general relativity. In cosmological studies, for example, physicists routinely model whole galaxies as if they are points, since their size, in relation to the whole of the universe, is extremely tiny. For this reason, implementing Riemann's geometrical framework in this crude manner proves to be a very accurate approximation, as evidenced by the success of general relativity in a cosmological context. But in the ultramicroscopic realm, the extended nature of the string ensures that Riemann's geometry simply will not be the right mathematical formalism. Instead, as we will now see, it must be replaced by the quantum geometry of string theory, leading to dramatically new and unexpected properties, a cosmological playground. According to the Big Bang model of cosmology, the whole of the universe violently emerged from a singular cosmic explosion some 15 or so billion years ago. Today, as originally discovered by Hubble, we can see that the debris from this explosion, in the form of many billions of galaxies, is still streaming outward. The universe is expanding. We do not know whether this cosmic growth will continue forever, or if there will come a time when the expansion slows to a halt and then reverses itself, leading to a cosmic implosion. Astronomers and astrophysicists are trying to settle this question experimentally, since the answer turns on something that, in principle, can be measured: the average density of matter in the universe. If the average matter density exceeds a so-called critical density of about 1/100th of a billionth of a billionth of a billionth, 10^29, of a gram per cubic centimeter, about 5 hydrogen atoms for every cubic meter of the universe, then a large enough gravitational force will permeate the cosmos to halt and reverse the expansion. If the average matter density is less than the critical value, the gravitational attraction will be too weak to stop the expansion, which will continue forever. Based upon your own observations of the world, you might think that the average mass density of the universe greatly exceeds the critical value. But bear in mind that matter, like money, tends to clump. Using the average mass density of the Earth or the solar system, or even the Milky Way galaxy as an indicator for that of the whole universe, would be like using Bill Gates's net worth as an indicator of the average Earthling's finances. Just as there are many people whose net worth pales in comparison to that of Bill Gates, thereby diminishing the average enormously, there is a lot of nearly empty space between the galaxies that drastically lowers the overall average matter density. By carefully studying the distribution of galaxies throughout space, astronomers can get a pretty good handle on the average amount of visible matter in the universe. This turns out to be significantly less than the critical value, but there is strong evidence of both theoretical and experimental origin that the universe is permeated with dark matter. This is matter that does not participate in the processes of nuclear fusion that powers stars, and hence does not give off light. It is therefore invisible to the astronomer's telescope. No one has figured out the identity of the dark matter, let alone the precise amount that exists. The fate of our presently expanding universe, therefore, is as yet unclear. Just for argument's sake, let's assume that the mass density does exceed the critical value and that someday in the distant future the expansion will stop and the universe will begin to collapse upon itself. All galaxies will start to approach one another slowly, and then as time goes by, their speed of approach will increase until they rush together at blinding speed. You need to picture the whole of the universe squeezing together into an ever-shrinking cosmic mass. As in Chapter 3, from a maximum size of many billions of light-years, the universe will shrink to millions of light-years every moment, gaining speed as everything is crushed together to the size of a single galaxy, and then to the size of a single star, a planet, and down to the size of an orange, a pea, a grain of sand, and further, according to general relativity, to the size of a molecule, an atom, and in a final, inexorable cosmic crunch to no size at all. According to conventional theory, the universe began with a bang from an initial state of zero size, and if it has enough mass, it will end with a crunch to a similar state of ultimate cosmic compression. But when the distance scales involved are around the Planck length or less, quantum mechanics invalidates the equations of general relativity, as we are now well aware. We must instead make use of string theory, and so, whereas Einstein's general relativity allows the geometrical form of the universe to get arbitrarily small, in exactly the same way that the mathematics of Riemannian geometry allows an abstract shape to take on as small a size as the intellect can imagine, we are led to ask how string theory modifies the picture. As we shall now see, there is evidence that string theory once again sets a lower limit to physically accessible distance scales and, in a remarkably novel way, proclaims that the universe cannot be squeezed to a size shorter than the Planck length in any of its spatial dimensions. Based on the familiarity you now have with string theory, you might be tempted to hazard a guess as to how this comes about. After all, you might argue that no matter how many points you pile up on top of each other, point particles that is, their combined volume is still zero. By contrast, if these particles are really strings, collapsed together in completely random orientations, they will fill out a non-zero-sized blob, roughly like a Planck-sized ball of entangled rubber bands. If you made this argument, you would be on the right track, but you would be missing significant, subtle features that string theory elegantly employs to suggest a minimum size to the universe. These features serve to emphasize, in a concrete manner, the new stringy physics that comes into play and its resultant impact on the geometry of spacetime. To explain these important aspects, let's first call upon an example that pares away extraneous details without sacrificing the new physics. Instead of considering all 10 of the spacetime dimensions of string theory, or even the 4 extended spacetime dimensions we are familiar with, let's go back to the garden hose universe. We originally introduced this 2-spatial dimension universe in Chapter 8 in a pre-string context to explain aspects of Kaluza's and Klein's insights in the 1920s. Let's now use it as a cosmological playground to explore the properties of string theory in a simple setting. We will shortly use the insights we gained to better understand all of the spatial dimensions string theory requires. Toward this end, we imagine that the circular dimension of the garden hose universe starts out nice and plump, but then shrinks to shorter and shorter size, approaching the form of lineland, a simplified, partial version of the Big Crunch. The question we seek to answer is whether the geometrical and physical properties of this cosmic collapse have features that markedly differ between a universe based on strings and one based on point particles. The essential new feature. We do not have to search far to find the essential new string physics. A point particle moving in this two-dimensional universe can execute the kinds of motion illustrated in Figure 10.2. It can move along the extended dimension of the garden hose. It can move along the curled-up part of the garden hose, or any combination of the two. A loop of string can undergo similar motion, with one difference being that it oscillates as it moves around on the surface, as shown in Figure 10.3a. This is a distinction we have already discussed in some detail. The oscillations of the string imbue it with characteristics such as mass and force charges. Although a crucial aspect of string theory, this is not our present focus since we already understand its physical implications. Instead, our present interest is in another difference between point particle and string motion, a difference directly dependent on the shape of the space through which the string is moving. Since the string is an extended object, there is another possible configuration beyond those already mentioned. It can wrap around lasso, so to speak, the circular part of the garden hose universe. The string will continue to slide around and oscillate, but it will do so in this extended configuration. In fact, the string can wrap around the circular part of the space any number of times, as also shown in Figure 10.3b, and again will execute oscillatory motion as it slides around. When a string is in such a wrapped configuration, we say that it is in a winding mode of motion. Clearly, being in a winding mode is a possibility inherent to strings. There is no point-particle counterpart. We now seek to understand the implications of this qualitatively new kind of string motion on the string itself, as well as on the geometrical properties of the dimension it wraps. Throughout our previous discussion of string motion, we have focused on unwound strings. Strings that wrap around a circular component of space share almost all of the same properties as the strings we have studied. Their oscillations, just as those of their unwound counterparts, contribute strongly to their observed properties. The essential difference is that a wrapped string has a minimum mass, determined by the size of the circular dimension and the number of times it wraps around. The string's oscillatory motion determines a contribution in excess of this minimum. It is not difficult to understand the origin of this minimum mass. A wound string has a minimum length determined by the circumference of the circular dimension and the number of times the string encircles it. The minimum length of a string determines its minimum mass. The longer this length, the greater the mass, since there is more of it. Since the circumference of a circle is proportional to its radius, the minimum winding mode masses are proportional to the radius of the circle being wrapped. By using Einstein's E equals sign mc2, relating mass to energy, we can also say that the energy bound in a wound string is proportional to the radius of the circular dimension. Unwrapped strings also have a tiny minimum length, since if they didn't, we would be back in the realm of point particles. The same reasoning might lead to the conclusion that even unwrapped strings have a minuscule yet non-zero minimum mass. In a sense, this is true, but the quantum mechanical effects encountered in Chapter 6, remember, the Price is Right again, are able to exactly cancel this contribution to the mass. This is how, we recall, unwrapped strings can yield the zero-mass photon, graviton, and the other massless or near-massless particles, for example. Wrapped strings are different in this regard. How does the existence of wrapped string configurations affect the geometrical properties of the dimension around which the strings wind? The answer, first recognized in 1984 by the Japanese physicists Keiji Kakawa and Masami Yamasaki, is bizarre and remarkable. Let's consider the last cataclysmic stages of our variant on the Big Crunch in the garden hose universe. As the radius of the circular dimension shrinks to the Planck length and, in the mold of general relativity, continues to shrink to yet smaller lengths, string theory insists upon a radical reinterpretation of what actually happens. String theory claims that all physical processes in the garden hose universe, in which the radius of the circular dimension is shorter than the Planck length and is decreasing, are absolutely identical to physical processes in which the circular dimension is longer than the Planck length and increasing. This means that as the circular dimension tries to collapse through the Planck length and head toward ever smaller size, its attempts are made futile by string theory, which turns the tables on geometry. String theory shows that this evolution can be rephrased, exactly reinterpreted, as the circular dimension shrinking down to the Planck length and then proceeding to expand. String theory rewrites the laws of short-distance geometry so that what previously appeared to be complete cosmic collapse is now seen to be a cosmic bounce. The circular dimension can shrink to the Planck length. But because of the winding modes, attempts to shrink further actually result in expansion. Let's see why. The spectrum of string states. Some of the ideas in this and the next few sections are rather subtle, so don't be put off if you have trouble following every link in the explanatory chain, especially in a single reading. The new possibility of wound string configurations implies that the energy of a string in the garden hose universe comes from two sources: vibrational motion and winding energy. From the legacy of Kaluza and Klein, each depends on the geometry of the hose, that is, on the radius of its curled-up circular component, but with a distinctly stringy twist, since point particles cannot wrap around dimensions. Our first task, then, will be to determine precisely how the winding and vibrational contributions to the energy of a string depend on the size of the circular dimension. For this purpose, it proves convenient to separate the vibrational motion of strings into two categories: uniform and ordinary vibrations. Ordinary vibrations refer to the usual oscillations we have discussed repeatedly, such as those illustrated in Figure 6.2. Uniform vibrations refer to even simpler motion, the overall motion of string as it slides from one position to another without changing its shape. All string motion is a combination of sliding and oscillating, of uniform and ordinary vibrations. But for the present discussion, it is easier to separate them in this manner. In fact, the ordinary vibrations will not play a central part in our reasoning, and we will therefore include their effects only after we have finished giving the gist of the argument. Here are the two essential observations. First, uniform vibrational excitations of a string have energies that are inversely proportional to the radius of the circular dimension. This is a direct consequence of the quantum mechanical uncertainty principle. A smaller radius more strictly confines a string, and therefore, through quantum mechanical claustrophobia, increases the amount of energy in its motion. So, as the radius of the circular dimension decreases, the energy of motion of the string necessarily increases, the hallmark feature of an inverse proportionality. Second, as found in the preceding section, the winding mode energies are directly, not inversely, proportional to the radius. Remember, this is because the minimum length of wound strings, and hence their minimum energy, is proportional to the radius. These two observations establish that large values of the radius imply large winding energies and small vibration energies, whereas small values of the radius imply small winding energies and large vibration energies. This leads us to the key fact. For any large circular radius of the garden hose universe, there is a corresponding small circular radius for which the winding energies of strings in the former universe equal the vibration energies of strings in the latter, and vibration energies of strings in the former equal winding energies of strings in the latter. As physical properties are sensitive to the total energy of a string configuration, and not to how the energy is divided between vibration and winding contributions, there is no physical distinction between these geometrically distinct forms for the garden hose universe. And so, strangely enough, string theory claims that there is no difference whatsoever between a fat garden hose universe and a thin one. It's a cosmic hedging of bets, somewhat akin to what you, as a smart investor, should do if faced with the following puzzle. Imagine you learn that the fate of two stocks trading on Wall Street, say a company making fitness machines and a company making heart bypass valves, are inextricably connected. They each closed trading today valued at $1 per share, and you are told by a reliable source that if one company's stock goes up, the others will go down, and vice versa. Moreover, your source, who is completely trustworthy, but whose guidance might be crossing over legal boundaries, tells you that the next day's closing prices of these two companies are absolutely certain to be inversely related to one another. That is, if one stock closes at $2 per share, the other will close at 1 fas or 50 cents per share. If one stock closes at $10 per share, the other will close at $1/10, 10 cents per share, and so on. But the one thing your source can't tell you is which stock will close high and which will close low. What do? Well, you immediately invest all of your money in the stock market, equally divided between the shares of these two companies. As you can easily check by working out a few examples, no matter what happens on the next day, your investment cannot lose value. At worst, it can remain the same if both companies again close at $1, but any movement of share prices, consistent with your insider information, will increase your holdings. For instance, if the fitness company closes at $4 and the heart valve company closes at 25 cents, their combined value is $4.25 for each pair of shares, compared with $2 the previous day. Furthermore, from the perspective of net worth, it does not matter one bit whether the fitness company closes high and the heart valve company low, or vice versa. If you care only about the total amount of money, these two distinct circumstances are financially indistinguishable. The situation in string theory is analogous in that the energy in string configurations comes from two sources, vibrations and windings, whose contributions to the total energy of a string are generally different. But, as we shall see in more detail below, certain pairs of distinct geometrical circumstances, leading to high winding energy / low vibration energy, or low winding energy, high vibration energy, are physically indistinguishable. And, unlike the financial analogy for which considerations beyond total wealth can distinguish between the two types of stock holdings, there is absolutely no physical distinction between the two string scenarios. Actually, we shall see that to make the analogy with string theory tighter, we should consider what would happen if you did not divide your money equally between the two companies in your initial investment, but bought, say, 1,000 shares of the fitness company and 3,000 shares of the heart valve company. Now, the total value of your holdings does depend on which company closes high and which closes low. For instance, if the stocks close at $10, fitness, and 10 cents, heart valve, your initial investment of $4,000 will now be worth $10,300. If the reverse happens, the stocks close at 10 cents, fitness, and $10, heart valve, your holdings will be worth $30,100, significantly more. Nevertheless, the inverse relationship between the closing stock prices does ensure the following. If a friend of yours invests exactly opposite to you, 3,000 shares of the fitness company and 1,000 shares of the heart valve company, then the value of her holdings will be $10,300 if stocks close valves high / fitness low, the same as your holdings in the fitness high / valves low closing, and $30,100 if they close with fitness high / valves low, again the same as your holdings in the reciprocal situation. That is, from the point of view of total stock value, interchanging which stock closes high and which closes low is exactly compensated by interchanging the number of shares you own of each company. Hold this last observation in mind as we now return to string theory and think about the possible string energies in a specific example. Imagine that the radius of the circular garden hose dimension is, say, 10 times the Planck length. We will write this as R equals sine 10. A string can wrap around this circular dimension 1 time, 2 times, 3 times, and so forth. The number of times a string wraps around the circular dimension is called its winding number. The energy from winding, being determined by the length of wound string, is proportional to the product of the radius and the winding number. Additionally, for any amount of winding, the string can undergo vibrational motion. As the uniform vibrations we are currently focusing on have energies that are inversely dependent on the radius, they are proportional to whole number multiples of the reciprocal of the radius, 1r, which in this case is 1/10 of the Planck length. We call this whole number multiple the vibration number. As you can see, this situation is very similar to what we encountered on Wall Street, with the winding and vibration numbers being direct analogs of the shares held in the two companies, while R and 1R are the analogs of the closing prices per share in each. Now, just as you can easily calculate the total value of your investment from the number of shares held in each company and the closing prices, we can calculate the total energy carried by a string in terms of its vibration number, its winding number, and the radius. In Table 10.1, we give a partial list of these total energies for various string configurations, which we specify by their winding and vibration numbers, in a garden hose universe with radius r equals sine 10. A complete table would be infinitely long, since the winding and vibration numbers can take on arbitrary whole number values. But this representative piece of the table is adequate for our discussion. We see from the table and our remarks that we are in a high winding energy / low vibration energy situation. Winding energies come in multiples of 10, while vibrational energies come in multiples of the smaller number 1/10. Now imagine that the radius of the circular dimension shrinks, say, from 10 to 9.2 to 7.1, and on down to 3.4, 2.2, 2, 1.1, 0.7, all the way to 0.1, 1/10, where, for our present discussion, it stops. In this geometrically distinct form of the garden hose universe, we can compile an analogous table of string energies. Winding energies are now multiples of 1/10, while vibration energies are multiples of its reciprocal, 10. The results are shown in Table 10.2. At first glance, the two tables might appear to be different, but closer inspection reveals that although arranged in a different order, The total energy columns of both tables have identical entries. To find the corresponding entry in Table 10.2 for a chosen entry in Table 10.1com. 1 must simply interchange the vibration and winding numbers. That is, vibration and winding contributions play complementary roles when the radius of the circular dimension changes from 10 to 1/10. And so, as far as total string energies go, there is no distinction between these different sizes for the circular dimension. Just as the interchange of fitness high/valves low with valves high/fitness low is exactly compensated by an interchange of the number of shares held in each company, interchange of radius 10 and radius 1/10 is exactly compensated by the interchange of vibration and winding numbers. Moreover, while for simplicity we have focused on an initial radius of r equals sine 10 and its reciprocal 1/10, the conclusions drawn are the same for any choice of the radius and its reciprocal. Tables 10.1 and 10.2 are incomplete for two reasons. First, as mentioned, we have listed only a few of the infinite possibilities for winding vibration numbers that a string can assume. This, of course, poses no problem. We could make the tables as long as our patience allows and would find that the relation between them will continue to hold. Second, beyond winding energy, we have so far considered only energy contributions arising from the uniform vibrational motion of a string. We should now include the ordinary vibrations as well, since these give additional contributions to the string's total energy and also determine the force charges it carries. The important point, however, is that investigations have revealed that these contributions do not depend on the size of the radius. Thus, even if we were to include these more detailed features of string attributes in tables 10.1 and 10.2, the tables would still correspond exactly, since the ordinary vibrational contributions affect each table identically. We therefore conclude that the masses and the charges of particles in a garden hose universe with radius r are completely identical to those in a garden hose universe with radius 1r. And since these masses and force charges govern fundamental physics, there is no way to distinguish physically these two geometrically distinct universes. Any experiment done in one such universe has a corresponding experiment that can be done in the other, leading to exactly the same results. A debate. George and Gracie, after being flattened out into two-dimensional beings, take up residence as physics professors in the garden hose universe. After setting up their competing laboratories, each claims to have determined the size of the circular dimension. Surprisingly, although each has a reputation for carrying out research with great precision, their conclusions do not agree. George claims that the circular radius is r equals sine 10 times the Planck length, while Gracie claims that the circular radius is r equals 1 divided 10 times the Planck length. Gracie, says George, based on my string theory calculations, I know that if the circular dimension has radius 10, then I should expect to see strings whose energies are listed in Table 10.1. I have done extensive experiments using the new Planck energy accelerator, and they have revealed that this prediction is precisely confirmed. Therefore, with confidence, I claim that the circular dimension has radius r equals sine 10. Gracie, in defense of her claims, makes exactly the same remarks except for her conclusion that the list of energies in Table 10.2 is found, confirming that the radius is r equals 1 divided. Answer, which will also address the first of our three questions, highlights an important and subtle aspect of space and distance. Two interrelated notions of distance in string theory. Distance is such a basic concept in our understanding of the world that it is easy to underestimate the depth of its subtlety. With the surprising effects that special and general relativity have had on our notions of space and time, and the new features arising from string theory, we are led to be a bit more careful even in our definition of distance. The most meaningful definitions in physics are those that are operational. That is, definitions that provide a means, at least in principle, for measuring whatever is being defined. After all, no matter how abstract a concept is, having an operational definition allows us to boil down its meaning to an experimental procedure for measuring its value. How can we give an operational definition of the concept of distance? The answer to this question in the context of string theory is rather surprising. In 1988, the physicists Robert Brandenberger of Brown University and Kamran Vafa of Harvard University pointed out that if the spatial shape of a dimension is circular, there are two different yet related operational definitions of distance in string theory. Each lays out a distinct experimental procedure for measuring distance and is based, roughly speaking, on the simple principle that if a probe travels at a fixed and known speed, then we can measure a given distance by determining how long the probe takes to traverse it. The difference between the two procedures is the choice of probe used. The first definition uses strings that are not wound around a circular dimension, whereas the second definition uses strings that are wound. We see that the extended nature of the fundamental probe is responsible for there being two natural operational definitions of distance in string theory. In a point-particle theory, for which there is no notion of winding, there would be only one such definition. How do the results of each procedure differ? The answer found by Brandenberger and Vafa is as surprising as it is subtle. The rough idea underlying the result can be understood by appealing to the uncertainty principle. Unwound strings can move around freely and probe the full circumference of the circle, a length proportional to r. By the uncertainty principle, their energies are proportional to 1r. Recall from Chapter 6 the inverse relation between the energy of a probe and the distances to which it is sensitive. On the other hand, we have seen that wound strings have minimum energy proportional to r. As probes of distances, the uncertainty principle tells us that they are therefore sensitive to the reciprocal of this value, 1r. The mathematical embodiment of this idea shows that if each is used to measure the radius of a circular dimension of space, unwound string probes will measure r, while wound strings will measure 1r, where, as before, we are measuring distances in multiples of the Planck length. The result of each experiment has an equal claim to being the radius of the circle. What we learned from the string theory is that using different probes to measure distance can result in different answers. In fact, this property extends to all measurements of lengths and distances, not just to determining the size of a circular dimension. The results obtained by wound and unwound string probes will be inversely related to one another. If string theory describes our universe, why have we not encountered these two possible notions of distance in any of our day-to-day or scientific endeavors? Anytime we talk about distance, we do so in a manner that conforms to our experience of there being one concept of distance without any hint of there being a second notion. Why have we missed the alternative possibility? The answer is that although there is a high degree of symmetry in our discussion, whenever r, and hence 1r as well, differs significantly from the value 1, meaning again 1 times the Planck length, then one of our operational definitions proves extremely difficult to carry out, while the other proves extremely easy to carry out. In essence, we have always carried out the easy approach, completely unaware of there being another possibility. The discrepancy in difficulty between the two approaches is due to the very different masses of the probes used, high winding energy or low vibration energy, and vice versa. If the radius r, and hence 1r as well, differs significantly from the Planck length, that is, r equals sign 1, high energy here, for radii that are vastly different from the Planck length, corresponds to incredibly massive probes, billions and billions of times heavier than the proton, for instance, while low energy corresponds to probe masses at most a speck above zero. In such circumstances, there is a monumental difference in difficulty between the two approaches, since even producing the heavy string configurations is an undertaking that at present is beyond our technological prowess. In practice, then, only one of the two approaches is technologically feasible, the one involving the lighter of the two types of string configurations. This is the one used implicitly in all of our discussions involving distance encountered to this point. This is the one that informs and hence meshes with our intuition. Putting issues of practicality aside, in a universe governed by string theory, one is free to measure distances using either of the two approaches. When astronomers measure the size of the universe, they do so by examining photons that have traveled across the cosmos and have happened to enter their telescopes. No pun intended, photons are the light string modes in this situation. The result obtained is the 1061 times the Planck length quoted earlier. If the three familiar spatial dimensions are in fact circular and string theory is right, astronomers using vastly different and currently non-existent equipment, in principle, should be able to measure the extent of the heavens with heavy wound string modes and find a result that is the reciprocal of this huge distance. It is in this sense that we can think of the universe as being either huge, as we normally do, or terribly minute. According to the light string modes, the universe is large and expanding. According to the heavy modes, it is tiny and contracting. There is no contradiction here. Instead, we have two distinct but equally sensible definitions of distance. We are far more familiar with the first definition due to technological limitations, but nevertheless, each is an equally valid concept. Now, we can answer our earlier question about big humans in a little universe. When we measure the height of a human and find 6 feet, for instance, we necessarily use the light string modes. To compare their size to that of the universe, we must use the same measuring procedure, and, as above, this yields 15 billion light-years for the size of the universe, a result that is much larger than 6 feet. Asking how such a person can fit into the tiny universe as measured by the heavy string modes is asking a meaningless question. It's comparing apples and oranges. Since we now have two concepts of distance, using light or heavy string probes, we must compare measurements made in the same manner, a minimum size. It's been a bit of a trek, but we are now set for the key point. If one does stick to measuring distances the easy way, that is, using the lightest of the string modes instead of the heavy ones, the results obtained will always be larger than the Planck length. To see this, let's think through the hypothetical Big Crunch for the three extended dimensions, assuming them to be circular. For argument's sake, let's say that at the beginning of our thought experiment, unwound string modes are the light ones, and by using them it is determined that the universe has an enormously large radius and that it is shrinking in time. As it shrinks, these unwound modes get heavier and the winding modes get lighter. When the radius shrinks all the way to the Planck length, that is, when r takes on the value 1, the winding and vibration modes have comparable mass. The two approaches to measuring distance become equally difficult to carry out and, moreover, each would yield the same result since one is its own reciprocal. As the radius continues to shrink, the winding modes become lighter than the unwound modes, and hence, since we are always opting for the easier approach, they should now be used to measure distances. According to this method of measurement, which yields the reciprocal of that measured by the unwound modes, the radius is larger than 1 times the Planck length and increasing. This simply reflects that as r, the quantity measured by unwound strings, shrinks to 1 and continues to get smaller, 1r, the quantity measured by wound strings grows to 1 and gets larger. Therefore, if one takes care to always use the light string modes, the easy approach to measuring distance, the minimal value encountered is the Planck length. In particular, a Big Crunch to 0 size is avoided, as the radius of the universe as measured using light string mode probes is always larger than the Planck length. Rather than heading through the Planck length onto ever smaller size, the radius, as measured by the lightest string modes, decreases to the Planck length and then immediately starts to increase. The crunch is replaced by a bounce. Using light string modes to measure distances aligns with our conventional notion of length, the one that was around long before the discovery of string theory. It is according to this notion of distance, as seen in Chapter 5, that we encountered insurmountable problems with violent quantum undulations if sub-Planck scale distances play a physical role. We once again see, from this complementary perspective, that the ultra-short distances are avoided by string theory. In the physical framework of general relativity and in the corresponding mathematical framework of Riemannian geometry, there is a single concept of distance, and it can acquire arbitrarily small values. In the physical framework of string theory and, correspondingly, in the realm of the emerging discipline of quantum geometry, there are two notions of distance. By judiciously making use of both, we find a concept of distance that meshes with both our intuition and with general relativity when distance scales are large, but that differs from them dramatically when distance scales get small. Specifically, sub-Planck scale distances are inaccessible. As this discussion is quite subtle, let's re-emphasize one central point. If we were to spurn the distinction between easy and hard approaches to measuring length and, say, continue to use the unwound modes as r shrinks through the Planck length, it might seem that we would indeed be able to encounter a sub-Planck length distance. But the paragraphs above inform us that the word distance in the last sentence must be carefully interpreted, since it can have two different meanings, only one of which conforms to our traditional notion. And in this case, when r shrinks to sub-Planck length, but we continue to use the unwound strings, even though they have now become heavier than the wound strings, we are employing the hard approach to measuring distance, and hence the meaning of distance does not conform to our standard usage. However, the discussion is far more than one of semantics or even of convenience or practicality of measurement. Even if we choose to use the non-standard notion of distance and thereby describe the radius as being shorter than the Planck length, the physics we encounter, as discussed in previous sections, will be identical to that of a universe in which the radius, in the conventional sense of distance, is larger than the Planck length, as attested to, for example, by the exact correspondence between tables 10.1 and 10.2. And it is physics, not language, that really matters. Brandenburger, Waffe, and other physicists have made use of these ideas to suggest a rewriting of the laws of cosmology in which both the Big Bang and the possible Big Crunch do not involve a zero-size universe, but rather one that is Planck length in all dimensions. This is certainly a very appealing proposal for avoiding the mathematical, physical, and logical conundrums of a universe that emanates from or collapses to an infinitely dense point. Although it is conceptually difficult to imagine the whole of the universe compressed together into a tiny Planck-sized nugget, it is truly beyond the pale to imagine it crushed to a point of no size at all. String cosmology, as we shall discuss in Chapter 14, is a field very much in its infancy, but one that holds great promise, and may very well provide us with this easier-to-swallow alternative to the standard Big Bang model. How general is this conclusion? What if the spatial dimensions are not circular in shape? Do these remarkable conclusions about minimum spatial extent in string theory still hold? No one knows for sure. The essential aspect of circular dimensions is that they permit the possibility of wound strings. As long as the spatial dimensions, regardless of the details of their shape, allow strings to wind around them, most of the conclusions we have drawn should still apply. But what if, say, two of the dimensions are in the shape of a sphere? In this case, strings cannot get trapped in a wound configuration, because they can always slip off much as a stretched rubber band can pop off a basketball. Does string theory nevertheless limit the size to which these dimensions can shrink? Numerous investigations seem to show that the answer depends on whether a full spatial dimension is being shrunk, as in the examples in this chapter, or, as we shall encounter and explain in chapters 11 and 13, an isolated chunk of space is collapsing. The general belief among string theorists is that, regardless of shape, there is a minimum limiting size, much as in the case of circular dimensions, so long as we are shrinking a full spatial dimension. Establishing this expectation is an important goal for further research because it has a direct impact on a number of aspects of string theory, including its implications for cosmology. Mirror symmetry. Through general relativity, Einstein forged a link between the physics of gravity and the geometry of spacetime. At first blush, string theory strengthens and broadens the link between physics and geometry, since the properties of vibrating strings, their mass and the force charges they carry, are largely determined by the properties of the curled-up component of space. We have just seen, though, that quantum geometry, the geometry physics association in string theory, has some surprising twists. In general relativity and in conventional geometry, a circle of radius r is different from one whose radius is 1r, pure and simple, yet in string theory they are physically indistinguishable. This leads us to be bold enough to go further and ask whether there might be geometrical forms of space that differ in more drastic ways, not just in overall size but possibly also in shape, but that are nevertheless physically indistinguishable in string theory. In 1988, Lance Dixon of the Stanford Linear Accelerator Center made a pivotal observation in this regard that was further amplified by Wolfgang Lurch of CERN, Vafa at Harvard, and Nicholas Warner, then of the Massachusetts Institute of Technology. Based upon aesthetic arguments rooted in considerations of symmetry, these physicists made the audacious suggestion that it might be possible for two different Calabi-Yau shapes, chosen for the extra curled-up dimensions in string theory, to give rise to identical physics. To give you an idea of how this rather far-fetched possibility might actually occur, recall that the number of holes in the extra Calabi-Yau dimensions determines the number of families into which string excitations will arrange themselves. These holes are analogous to the holes one finds in a torus or its multi-handled cousins, as illustrated in Figure 9.1. One deficiency of the two-dimensional figure that we must show on the printed page is that it cannot show that a six-dimensional 10.4. The mathematics underlying the manipulations illustrated in Figure 10.4 is formidable, and for this reason string theorists had thoroughly investigated this procedure only as applied to the simplest of shapes, higher dimensional versions of the donut shapes shown in Figure 9.1. Plesser and I realized, though, that some beautiful new insights of Doron Gepner, then of Princeton University, might give a powerful theoretical framework for applying the orbifolding technique to full-fledged Calabi-Yau shapes, such as the one in Figure 8.9. After a few months of intensive pursuit of this idea, we came to a surprising realization. If we glued particular groups of points together in just the right way, the Calabi-Yau shape we produced differed from the one we started with in a startling manner. The number of odd-dimensional holes in the new Calabi-Yau shape equaled the number of even-dimensional holes in the original, and vice versa. In particular, this means that the total number of holes, and therefore the number of particle families in each, is the same, even though the even-odd interchange means that their shapes and fundamental geometrical structures are quite different. Excited by the apparent contact we had made with the Dixon-Lurch-Vafa-Warner guess, Plesser and I pressed on to the linchpin question. Beyond the number of families of particles, do the two different Calabi-Yau spaces agree on the rest of their physical properties? After a couple more months of detailed and arduous mathematical analysis, during which we received valuable inspiration and encouragement from Graham Ross, my thesis advisor at Oxford, and also from Vafa, Plesser and I were able to argue that the answer was, most definitely, yes. For mathematical reasons having to do with the even-odd interchange, Plesser and I coined the term mirror manifolds to describe the physically equivalent yet geometrically distinct Calabi-Yau spaces. The individual spaces in a mirror pair of Calabi-Yau spaces are not literally mirror images of one another, in the sense of everyday usage. But even though they have different geometrical properties, they give rise to one and the same physical universe when used for the extra dimensions in string theory. The weeks after finding this result were an extremely anxious time. Plesser and I knew that we were sitting on an important new piece of string physics. We had shown that the tight association between geometry and physics originally set down by Einstein was substantially modified by string theory. Drastically different geometrical shapes that would imply different physical properties in general relativity were giving rise to identical physics in string theory. But what if we had made a mistake? What if their physical implications did differ in some subtle way that we had missed? When we showed our results to Yau, for example, he politely but firmly claimed that we must have made an error. He asserted that from a mathematical standpoint our results were far too outlandish to be true. His assessment gave us substantial pause. It's one thing to make a mistake in a small or modest claim that attracts little attention. Our result, though, was suggesting an unexpected step in a new direction that would certainly engender a strong response. If it were wrong, everyone would know. Finally, after much checking and rechecking, our confidence grew and we sent our paper off for publication. A few days later, I was sitting in my office at Harvard and the phone rang. It was Philip Candelas from the University of Texas, and he immediately asked me if I was seated. I was. He then told me that he and two of his students, Monica Linker and Rolf Schimrick, had found something that was going to knock me off of my chair. By carefully examining a huge sample set of Calabi-Yau spaces that they had generated by computer, they found that almost all came in pairs, differing precisely by the interchange of the number of even and odd holes. I told him that I was still seated, that Plesser and I had found the same result. Candelas's and our work turned out to be complementary. We had gone one step further by showing that all of the resulting physics in a mirror pair was identical, whereas Candelas and his students had shown that a significantly larger sample of Calabi-Yau shapes fell into mirror pairs. Through the two papers, we had discovered the mirror symmetry of string theory, the physics and the mathematics of mirror symmetry. The loosening of Einstein's rigid and unique association between the geometry of space and observed physics is one of the striking paradigm shifts of string theory. But these developments entail far more than a change in philosophical stance. Mirror symmetry, in particular, provides a powerful tool for understanding both the physics of string theory and the mathematics of Calabi-Yau spaces. Mathematicians working in a field called algebraic geometry had been studying Calabi-Yau spaces for purely mathematical reasons long before string theory was discovered. They had worked out many of the detailed properties of these geometrical spaces without an inkling of a future physical application. Certain aspects of Calabi-Yau spaces, however, had proven difficult, essentially impossible, for mathematicians to unravel fully. But the discovery of mirror symmetry in string theory changed this significantly. In essence, mirror symmetry proclaims that particular pairs of Calabi-Yau spaces, pairs that were previously thought to be completely unrelated, are now intimately connected by string theory. They are linked by the common physical universe each implies if either is the one selected for the extra curled-up dimensions. This previously unsuspected interconnection provides an incisive new physical and mathematical tool. Imagine, for instance, that you are busily calculating the physical properties, particle masses, and force charges associated with one possible Calabi-Yau choice for the extra dimensions. You are not particularly concerned with matching your detailed results with experiment, since as we have seen, a number of theoretical and technological obstacles make doing this quite difficult at present. Instead, you are working through a thought experiment concerned with what the world would look like if a particular Calabi-Yau space were selected. For a while, everything is going along fine, but then, in the midst of your work, you come upon a mathematical calculation of insurmountable difficulty. No one, not even the world's most expert mathematicians, can figure out how to proceed. You are stuck. But then you realize that this Calabi-Yau has a mirror partner. Since the resulting string physics associated with each member of a mirror pair is identical, you recognize that you are free to do your calculations making use of either. And so, you rephrase the difficult calculation on the original Calabi-Yau space in terms of a calculation on its mirror, assured that the result of the calculation, the physics, will be the same. At first sight, you might think that the rephrased version of the calculation will be as difficult as the original. But here you come upon a pleasant and powerful surprise. You discover that although the result will be the same, the detailed form of the calculation is very different, and in some cases the horribly difficult calculation you started with turns into an extremely easy calculation on the mirror Calabi-Yau space. There is no simple explanation for why this happens, but, at least for certain calculations, it most definitely does, and the decrease in level of difficulty can be dramatic. The implication, of course, is clear. You are no longer stuck. It's somewhat as if someone requires you to count exactly the number of oranges that are haphazardly jumbled together in an enormous bin, some 50 feet on each side and 10 feet deep. You start to count them one by one, but soon realize that the 117,206,375. Ellingsrud and Strom announced the result of their very difficult mathematical calculation. 2,682,549,425. For days, mathematicians and physicists debated who was right. The question turned into a real litmus test of the quantitative reliability of string theory. A number of people even commented, somewhat in jest, that this test was the next best thing to being able to compare string theory with experiment. Moreover, Candelas's results went far beyond the single numerical result that Ellingsrud and Strom claimed to have calculated. He and his collaborators claim to have also answered many other questions that were tremendously more difficult. So difficult, in fact, that no mathematician had ever even attempted to address them. But could the string theory results be trusted? The meeting ended with a great deal of fruitful exchange between mathematicians and physicists, but no resolution of the discrepancy. About a month later, an email message was widely circulated among participants in the Berkeley meeting with the subject heading "Physics Wins." Ellingsrud and Straume had found an error in their computer code that, when corrected, confirmed Candelas's result. Since then, there have been many mathematical checks on the quantitative reliability of the mirror symmetry of string theory. It has passed all with flying colors. Even more recently, almost a decade after physicists discovered mirror symmetry, mathematicians have made great progress in revealing its inherent mathematical foundations. By utilizing substantial contributions of the mathematicians Maxim Kontsevich, Yuri Manin, Gang Tian, Jun Li, and Alexander Giventhal, Yao and his collaborators Bong Lian and Keifeng Liu have finally found a rigorous mathematical proof of the formulas used to count spheres inside Calabi-Yau spaces, thereby solving problems that have puzzled mathematicians for hundreds of years. Beyond the particulars of this success, what these developments really highlight is the role that physics has begun to play in modern mathematics. For quite some time, physicists have mined mathematical archives in search of tools for constructing and analyzing models of the physical world. Now, through the discovery of string theory, physics is beginning to repay the debt and to provide mathematicians with powerful new approaches to their unsolved problems. String theory not only provides a unifying framework for physics, but it may well forge an equally deep union with mathematics as well. Chapter 11. Tearing the Fabric of Space. If you relentlessly stretch a rubber membrane, sooner or later it will tear. This simple fact has inspired numerous physicists over the years to ask whether the same might be true of the spatial fabric making up the universe. That is, can the fabric of space rip apart, or is this merely a misguided notion that arises from taking the rubber membrane analogy too seriously? Einstein's general relativity says no, the fabric of space cannot tear. The equations of general relativity are firmly rooted in Riemannian geometry, and, as we noted in the preceding chapter, this is a framework that analyzes distortions in the distance relations between nearby locations in space. In order to speak meaningfully about these distance relations, the underlying mathematical formalism requires that the substrate of space is smooth, a term with a technical mathematical meaning but whose everyday usage captures its essence. No creases, no punctures, no separate pieces stuck together, and no tears. Were the fabric of space to develop such irregularities, the equations of general relativity would break down, signaling some or other variety of cosmic catastrophe, a disastrous outcome that our apparently well-behaved universe avoids. This has not kept imaginative theorists over the years from pondering the possibility that a new formulation of physics that goes beyond Einstein's classical theory and incorporates quantum physics might show that rips, tears, and mergers of the spatial fabric can occur. In fact, the realization that quantum physics leads to violent short-distance undulations led some to speculate that rips and tears might be a commonplace microscopic feature of the spatial fabric. The concept of wormholes, a notion with which any fan of Star Trek Deep Space Nine is familiar, makes use of such musings. The idea is simple. Imagine you're the CEO of a major corporation with headquarters on the 90th floor of one of New York City's World Trade Center towers. Through the vagaries of corporate history, an arm of your company with which you need to have ever-increasing contact is ensconced on the 90th floor of the other tower. As it is impractical to move either office, you come up with a natural suggestion. Build a bridge from one office to the other, connecting the two towers. This allows employees to move freely between the offices without having to go down and then up 90 floors. A wormhole plays a similar role. It is a bridge or tunnel that provides a shortcut from one region of the universe to another. Using a two-dimensional model, imagine that a universe is shaped as in Figure 11.1. If your corporate headquarters are located near the lower circle in 11.1a, you can get to your field office, located near the upper circle, only by traversing the entire U-shaped path, taking you from one end of the universe to another. But if the fabric of space can tear, developing punctures as in 11.1b, and if these punctures can grow tentacles that merge together as in 11.1c, a spatial bridge would connect the previously remote regions. This is a wormhole. You should note that the wormhole has some similarity to the World Trade Center bridge. But there is one essential difference. The World Trade Center bridge would traverse a region of existing space, the space between the two towers. On the contrary, the wormhole creates a new region of space, since the curved two-dimensional space in Figure 11.1a is all there is, in the setting of our two-dimensional analogy. Regions lying off of the membrane merely reflect the inadequacy of the illustration, which depicts the U-shaped universe as if it were an object within our higher dimensional universe. The wormhole creates new space and therefore blazes new spatial territory. Do wormholes exist in the universe? No one knows, and if they do, it is far from clear whether they would take on only a microscopic form or if they could span vast regions of the universe, as in Deep Space Nine. But one essential element in assessing whether they are fact or fiction is determining whether or not the fabric of space can tear. Black holes provide another compelling example in which the fabric of space is stretched to its limits. In Figure 3.7, we saw that the enormous gravitational field of a black hole results in such extreme curvature that the fabric of space appears to be pinched or punctured at the black hole's center. Unlike in the case of wormholes, there is strong experimental evidence supporting the existence of black holes, so the question of what really happens at their central point is one of science, not speculation. Once again, the equations of general relativity break down under such extreme conditions. Some physicists have suggested that there really is a puncture, but that we are protected from this cosmic singularity by the event horizon of the black hole, which prevents anything from escaping its gravitational grip. This reasoning led Roger Penrose of Oxford University to speculate on a cosmic censorship hypothesis that allows these kinds of spatial irregularities to occur only if they are deeply hidden from our view behind the shroud of an event horizon. On the other hand, prior to the discovery of string theory, some physicists surmised that a proper merger of quantum mechanics and general relativity would show that the apparent puncture of space is actually smoothed out, sewn up, so to speak, by quantum considerations. With the discovery of string theory and the harmonious merger of quantum mechanics and gravity, we are finally poised to study these issues. As yet, string theorists have not been able to answer them fully, but during the last few years, closely related issues have been solved. In this chapter, we discuss how string theory, for the first time, definitively shows that there are physical circumstances, differing from wormholes and black holes in certain ways, in which the fabric of space can tear. A tantalizing possibility. In 1987, Xing-Tung Yao and his student Gong Tian, now at the Massachusetts Institute of Technology, made an interesting mathematical observation. They found, using a well-known mathematical procedure, that certain Calabi-Yau shapes could be transformed into others by puncturing their surface and then sewing up the resulting hole according to a precise mathematical pattern. Roughly speaking, they identified a particular kind of two-dimensional sphere, like the surface of a beach ball, sitting inside an initial Calabi-Yau space, as in Figure 11.2. A beach ball, like all familiar objects, is three-dimensional. Here, however, we are referring solely to its surface. We are ignoring the thickness of the material from which it is made as well as the interior space it encloses. Points on the beach ball's surface can be located by giving two numbers, latitude and longitude, much as we locate points on the Earth's surface. This is why the surface of the beach ball, like the surface of the garden hose discussed in preceding chapters, is two-dimensional. They then considered shrinking the sphere until it is pinched down to a single point, as we illustrate with the sequence of shapes in Figure 11.3. This figure, and subsequent ones in this chapter, have been simplified by focusing in on the most relevant piece of the Calabi-Yau shape. But in the back of your mind, you should note that these shape transformations are occurring within a somewhat larger Calabi-Yau space, as in Figure 11.2. And finally, Tian and Yao imagined slightly tearing the Calabi-Yau space at the pinch, opening it up and gluing in another beach ball-like shape, which they could then reinflate to a nice plump form. Mathematicians call this sequence of manipulations a flop transition. It's as if the original beach ball shape is flopped over into a new orientation within the overall Calabi-Yau shape. Yau, Tian, and others noted that under certain circumstances the new Calabi-Yau shape produced by a flop, as in Figure 11.4, D, is topologically distinct from the initial Calabi-Yau shape in Figure 11.3, A. This is a fancy way of saying that there is absolutely no way to deform the initial Calabi-Yau space in Figure 11.3, A, into the final Calabi-Yau space shown in Figure 11.4, D, without tearing the fabric of the Calabi-Yau space at some intermediate stage. From a mathematical standpoint, this procedure of Yau and Tian is of interest because it provides a way to produce new Calabi-Yau spaces from ones that are known, but its real potential lies in the realm of physics, where it raises a tantalizing question. Could it be that, beyond its being an abstract mathematical procedure, the sequence displayed from Figure 11.3, A through Figure 11.4, D, might actually occur in nature? Might it be that, contrary to Einstein's expectations, the fabric of space can tear apart and subsequently be repaired in the manner described? The mirror perspective. For a couple of years after their 1987 observation, Yau would, every so often, encourage me to think about the possible physical incarnation of these flop transitions. I didn't. To me, it seemed that flop transitions were merely a piece of abstract mathematics without any bearing on the physics of string theory. In fact, based on the discussion in Chapter 10 in which we found that circular dimensions have a minimum radius, one might be tempted to say that string theory does not allow the sphere in Figure 11.3 to shrink all the way down to a pinched point. But remember, as also noted in Chapter 10, that if a chunk of space collapses, in this case a spherical piece of a Calabi-Yau shape, as opposed to the collapse of a complete spatial dimension, the argument identifying small and large radii is not directly applicable. Nevertheless, even though this idea for ruling out flop transitions does not stand up to scrutiny, the possibility that the fabric of space could tear still seemed rather unlikely. But then, in 1991, the Norwegian physicist Andy Lutken, together with Paul Aspinwall, a graduate school classmate of mine from Oxford and now a professor at Duke University, asked themselves what proved to be a very interesting question. If the spatial fabric of the Calabi-Yau portion of our universe were to undergo a space-tearing flop transition, what would it look like from the perspective of the mirror Calabi-Yau space? To understand the motivation for this question, you must recall that the physics emerging from either member of a mirror pair of Calabi-Yau shapes, if selected for the extra dimensions, is identical, but the complexity of the mathematics that a physicist must employ to extract the physics can differ significantly between the two. Aspinwall and Lutken speculated that the mathematically complicated flop transition of figures 11.3 and 11.4 might have a far simpler mirror description, one that might give a more transparent view on the associated physics. At the time of their work, mirror symmetry was not understood at the depth required to answer the question they posed. However, Aspinwall and Lutken noted that there did not seem to be anything in the mirror description that would indicate a disastrous physical consequence associated with the spatial tiers of flop transitions. Around the same time, the work Plesser and I had done in finding mirror pairs of Calabi-Yau shapes, see Chapter 10, unexpectedly led us to think about flop transitions as well. It is a well-known mathematical fact that gluing various points together, as in Figure 10.4, the procedure we had used to construct mirror pairs, leads to geometrical situations that are identical to the pinch and puncture in Figures 11.3 and 11.4. Physically, though, Plesser and I could find no associated calamity. Moreover, inspired by the observations of Aspinwall and Lutken, as well as a previous paper of theirs with Graham Ross, Plesser and I realized that we could repair the pinch mathematically in two different ways. One way led to the Calabi-Yau shape in Figure 11.3, A, while the other led to that in Figure 11.4, D. This suggested to us that the evolution from figure 11.3, A, through figure 11.4, D, was something that could actually occur in nature. By late 1991, then, at least a few string theorists had a strong feeling that the fabric of space can tear, but no one had the technical facility to definitively establish or refute this striking possibility. Inching forward. Off and on during 1992, Plesser and I tried to show that the fabric of space can undergo space-tearing flop transitions. Our calculations yielded bits and pieces of supporting circumstantial evidence, but we could not find definitive proof. Sometime during the spring, Plesser visited the Institute for Advanced Study in Princeton to give a talk, and privately told Witten about our recent attempts to realize the mathematics of space-tearing flop transitions within the physics of string theory. After summarizing our ideas, Plesser waited for Witten's response. Witten turned from the blackboard and stared out of his office window. After a minute of silence, maybe two, he turned back to Plesser and told him that if our ideas worked out, it would be spectacular. This rekindled our efforts. But after a while, with our progress stalled, each of us turned to working on other string theory projects. Even so, I found myself mulling over the possibility of space-tearing flop transitions. As the months went by, I felt increasingly sure that they had to be part and parcel of string theory. The preliminary calculations Plesser and I had done, together with insightful discussions with David Morrison, a mathematician from Duke University, made it seem that this was the only conclusion that mirror symmetry naturally supported. In fact, during a visit to Duke, Morrison and I, together with some helpful observations from Sheldon Katz of Oklahoma State University, who was also visiting Duke at the time, outlined a strategy for proving that flop transitions can occur in string theory. But when we sat down to do the required calculations, we found that they were extraordinarily intensive. Even on the world's fastest computer, they would take more than a century to complete. We had made progress, but we clearly needed a new idea, one that could greatly enhance the efficiency of our calculational method. Unwittingly, Viktor Batirev, a mathematician from the University of Essen, revealed such an idea through a pair of papers released in the spring and summer of 1992. Batirev had become very interested in mirror symmetry, especially in the wake of the success of Kandalas and his collaborators in using it to solve the sphere counting problem described at the end of Chapter 10. With a mathematician's perspective, though, Batirev was unsettled by the methods Plesser and I had invoked to find mirror pairs of Calabi-Yau spaces. Although our approach used tools familiar to string theorists, Batirev later told me that our paper seemed to him to be black magic. This reflects the large cultural divide between the disciplines of physics and mathematics, and as string theory blurs their borders, the vast differences in language, methods, and styles of each field become increasingly apparent. Physicists are more like avant-garde composers, willing to bend traditional rules and brush the edge of acceptability in the search for solutions. Mathematicians are more like classical composers, typically working within a much tighter framework, reluctant to go to the next step until all previous ones have been established with due rigor. Each approach has its advantages as well as drawbacks. Each provides a unique outlet for creative discovery. Like modern and classical music, it's not that one approach is right and the other wrong. The methods one chooses to use are largely a matter of taste and training. Batirev set out to recast the construction of mirror manifolds in a more conventional mathematical framework, and he succeeded. Inspired by earlier work of Shi-Shir Rowan, a mathematician from Taiwan, he found a systematic mathematical procedure for producing pairs of Calabi-Yau spaces that are mirrors of one another. His construction reduces to the procedure Plesser and I had found in the examples we had considered, but offers a more general framework that is phrased in a manner more familiar to mathematicians. The flip side is that Batirev's papers invoked areas of mathematics that most physicists had never previously encountered. I, for example, could extract the gist of his arguments, but had significant difficulty in understanding many crucial details. One thing, however, was clear. The methods of his paper, if properly understood and applied, could very well open a new line of attack on the issue of space-tearing flop transitions. By late summer, energized by these developments, I decided that I wanted to return to the problem of flops with full and undistracted intensity. I had learned from Morrison that he was going on leave from Duke to spend a year at the Institute for Advanced Study, and I knew that Aspinwall would also be there, as a postdoctoral fellow. After a few phone calls and emails, I arranged to take leave from Cornell University and spend the fall of 1992 at the Institute as well. A strategy emerges, dramatically illustrated in Figure 1, 1.5 comma, in which the top row is the original evolution from Figure 11.3 A to Figure 11.4 D, and the bottom row is the same evolution from the perspective of the mirror Calabi-Yau shapes. As a number of us had already realized, it turns out that in the mirror rephrasing it appears that string physics is perfectly well behaved and encounters no catastrophes. As you can see, there does not seem to be any pinching or tearing in the bottom row in Figure 11.5. However, the real question this observation raised for us was this: were we pushing mirror symmetry beyond the bounds of its applicability? Although the upper and lower Calabi-Yau shapes drawn on the far left-hand side of Figure 11.5 yield identical physics, is it true that at every step in the evolution to the right-hand side of Figure 11.5, necessarily passing through the pinch-tear repair stage in the middle, the physical properties of the original and mirror perspective are identical? Although we had solid reason to believe that the powerful mirror relationship holds for the shape progression leading to the tear in the upper Calabi-Yau shape in Figure 11.5 comma. We realized that no one knew whether the upper and lower Calabi-Yau shapes in Figure 11.5 continue to be mirrors after the tear has occurred. This is a crucial question, because if they are, then the absence of a catastrophe in the mirror perspective would mean an absence in the original, and we would have demonstrated that space can tear in string theory. We realized that this question could be reduced to a calculation. Extract the physical properties of the universe for the upper Calabi-Yau shape after the tear, using, say, the upper right Calabi-Yau shape in Figure 11.5, and for its supposed mirror, the lower right Calabi-Yau shape in Figure 11.5, and see if they are identical. It was this calculation to which Aspinwall, Morrison, and I devoted ourselves in the fall of 1992, late nights at Einstein's final stomping ground. Edward Witten's razor-sharp intellect is clothed in a soft-spoken demeanor that often has a wry, almost ironic edge. He is widely regarded as Einstein's successor in the role of the world's greatest living physicist. Some would go even further and describe him as the greatest physicist of all time. He has an insatiable appetite for cutting-edge physics problems, and he wields tremendous influence in setting the direction of research in string theory. The breadth and depth of Witten's productivity is legendary. His wife, Chiara Nappi, who is also a physicist at the Institute, paints a picture of Witten sitting at their kitchen table, mentally probing the edge of string theory knowledge, and only now and then returning to pick up pen and paper to verify an elusive detail or two. Another story is told by a postdoctoral fellow who, one summer, had an office next to Witten's. He describes the unsettling juxtaposition of laboriously struggling with complex string theory calculations at his desk while hearing the incessant rhythmic patter of Witten's keyboard, as paper after groundbreaking paper poured forth directly from mind to computer file. A week or so after I arrived, Witten and I were chatting in the Institute's courtyard, and he asked about my research plans. I told him about the space-tearing flops and the strategy we were planning to pursue. He lit up upon hearing the ideas, but cautioned that he thought the calculations would be horrendously difficult. He also pointed out a potential weak link in the strategy I described, having to do with some work I had done a few years earlier with Vafa and Warner. The issue be raised turned out to be only tangential to our approach for understanding flops, but it started him thinking about what ultimately turned out to be related and complementary issues. Aspinwall, Morrison, and I decided to split our calculation in two pieces. At first, a natural division might have seemed to involve first extracting the physics associated with the final Calabi-Yau shape from the upper row of Figure 11.5 comma, and then doing the same for the final Calabi-Yau shape from the lower row of Figure 11.5. If the mirror relationship is not shattered by the tear in the upper Calabi-Yau, then these two final Calabi-Yau shapes should yield identical physics, just like the two initial Calabi-Yau shapes from which they evolved. This way of phrasing the problem avoids doing any of the very difficult calculations involving the upper Calabi-Yau shape just when it tears. It turns out, though, that calculating the physics associated with the final Calabi-Yau shape in the upper row is pretty straightforward. The real difficulty in carrying out this program lies in first figuring out the precise shape of the final Calabi-Yau space in the lower row of Figure 11.5, the putative mirror of the upper Calabi-Yau of six-packs and working weekends. Nothing focuses the mind of a physicist like a healthy dose of competition. Aspinwall, Morrison, and I went into high gear. It's important to note that this meant one thing to Morrison and me, and quite another to Aspinwall. Aspinwall is a curious mixture of upper-class British sensibility, largely a reflection of the decade he spent at Oxford as both an undergraduate and a graduate student, infused ever so slightly with a prankster's roguishness. As far as work habits go, he is perhaps the most civilized physicist I know. While many of us work deep into the evening, he never works past 5 p.m. While many of us work weekends, Aspinwall does not. He gets away with this because he is both sharp and efficient. Going into high gear for him merely amounts to notching up his efficiency level to even greater heights. By this time, it was early December. Morrison and I had been lecturing to one another for several months, and it was starting to pay off. We were very close to being able to identify the precise shape of the Calabi-Yau space we were seeking. Moreover, Aspinwall had just about finished his computer code, and he now awaited our result, which would be the required input for his program. It was a Thursday night when Morrison and I finally had confidence that we knew how to identify the sought-after Calabi-Yau shape. That, too, boiled down to a procedure that required its own, fairly simple computer code. By Friday afternoon, we had written the program and debugged it. By late Friday night, we had our result, but it was after 5 p.m., and it was Friday. Aspinwall had gone home and would not return until Monday. There was nothing we could do without his computer code. Neither Morrison nor I could imagine waiting out the whole weekend. We were on the verge of answering the long-pondered question of spatial tiers in the fabric of the cosmos, and the suspense was too much to bear. We called Aspinwall at home. At first he refused to come to work the next morning as we asked, but then, after much groaning, he consented to join us as long as we bought him a six-pack of beer. We agreed. A moment of truth. We all met at the Institute Saturday morning as planned. It was a bright sunny morning, and the atmosphere was jokingly relaxed. I, for one, half expected that Aspinwall would not show up. Once he did, I spent 15 minutes extolling the import of this first weekend he had come into the office. He assured me it wouldn't happen again. We all huddled around Morrison's computer in the office he and I shared. Aspinwall told Morrison how to bring his program up on the screen and showed us the precise form for the required input. Morrison appropriately formatted the results we had generated the previous night, and we were set to go. The particular calculation we were performing amounts, roughly speaking, to determining the mass of a certain particle species, a specific vibrational pattern of a string, when moving through a universe whose Calabi-Yau component we had spent all fall identifying. We hoped, in line with the strategy discussed earlier, that this mass would agree identically with a similar calculation done on the Calabi-Yau shape emerging from the space-tearing flop transition. The latter was the relatively easy calculation, and we had completed it weeks before. The answer turned out to be 3, in the particular units we were using. Since we were now doing the purported mirror calculation numerically on a computer, we expected to get something extremely close to, but not exactly 3, something like 3.0000001 or 2.999999, comma, with the tiny difference arising from rounding errors. Morrison sat at the computer with his finger hovering over the Enter button. With the tension mounting, he said, "Here goes," and set the calculation in motion. In a couple of seconds, the computer returned its answer, 8.999999. My heart sank. Could it be that space-tearing flop transitions shatter the mirror relation, likely indicating that they cannot actually occur? Almost immediately, though, we all realized that something funny must be going on. If there was a real mismatch in the physics following from the two shapes, it was extremely unlikely that the computer calculation should yield an answer so close to a whole number. If our ideas were wrong, there was no reason in the world to expect anything but a random collection of digits. We had gotten a wrong answer, but one that suggested, perhaps, that we had just made some simple arithmetic error. Aspinwall and I went to the blackboard, and in a moment we found our mistake. We had dropped a factor of 3 in the simpler calculation we had done weeks before. The true result was 9. The computer answer was therefore just what we wanted. Of course, the after-the-fact agreement was only marginally convincing. When you know the answer you want, it is often all too easy to figure out a way of getting it. We needed to do another example. Having already written all of the necessary computer code, this was not hard to do. We calculated another particle mass on the upper Calabi-Yau shape, being careful this time to make no errors. We found the answer: 12. Once again, we huddled around the computer and set it on its way. Seconds later, it returned 11.999999. Agreement. We had shown that the supposed mirror is the mirror, and hence space-tearing flop transitions are part of the physics of string theory. At this, I jumped out of my chair and ran an unrestrained victory lap around the office. Morrison beamed from behind the computer. Aspinwall's reaction, though, was rather different. "That's great, but I knew it would work," he calmly said. "And where's my beer?" Witten's approach. That Monday, we triumphantly went to Witten and told him of our success. He was very pleased with our result, and as it turned out, he too had just found a way of establishing that flop transitions occur in string theory. His argument was quite different from ours, and it significantly illuminates the microscopic understanding of why the spatial tears do not have any catastrophic consequences. His approach highlights the difference between a point-particle theory and string theory when such tears occur. The key distinction is that there are two types of string motion near the tear, but only one kind of point-particle motion. Namely, a string can travel adjacent to the tear, like a point particle does, but it can also encircle the tear as it moves forward, as illustrated in Figure 11.6. In essence, Witten's analysis reveals that strings which encircle the tear, something that cannot happen in a point-particle theory, shield the surrounding universe from the catastrophic effects that would otherwise be encountered. It's as if the world sheet of the string— recall from Chapter 6 that this is a two-dimensional surface that a string sweeps out as it moves through space— provides a protective barrier that precisely cancels out the calamitous aspects of the geometrical degeneration of the spatial fabric. You might well ask, what if such a tear should occur, and it just so happens that there are no strings in the vicinity to shield it? Moreover, you might also be concerned that at the instant in time that a tear occurs, a string, an infinitely thin loop, would provide as effective a barrier as shielding yourself from a cluster bomb by hiding behind a hula hoop. The resolution to both of these issues relies on a central feature of quantum mechanics that we discussed in Chapter 4. There, we saw that in Feynman's formulation of quantum mechanics, an object, be it a particle or a string, travels from one location to another by sniffing out all possible trajectories. The resulting motion that is observed is a combination of all possibilities, with the relative contributions of each possible trajectory precisely determined by the mathematics of quantum mechanics. Should a tear in the fabric of space occur, then, among the possible trajectories of traveling strings are those that encircle the tear trajectories, such as those in Figure 11.6. Even if no strings seem to be near the tear when it occurs, quantum mechanics takes account of physical effects from all possible string trajectories, and among these are numerous, infinite in fact, protective paths that encircle the tear. It is these contributions that Witten showed precisely to cancel out the cosmic calamity that the tear would otherwise create. In January 1993, Witten and the three of us released our papers simultaneously to the Electronic Internet Archive, through which physics papers are immediately made available worldwide. The two papers described, from our widely different perspectives, the first examples of topology-changing transitions, the technical name for the space-tearing processes we had found. The long-standing question about whether the fabric of space can tear had been settled quantitatively by string theory. Consequences. We have made much of the realization that spatial tears can occur without physical calamity. But what does happen when the spatial fabric rips? What are the observable consequences? We have seen that many properties of the world around us depend upon the detailed structure of the curled-up dimensions. And so, you would think that the fairly drastic transformation from one Calabi-Yau to another, as shown in Figure 1, 1.5, would have a significant physical impact. In fact, though, the lower dimensional drawings that we use to visualize the spaces make the transformation appear to be somewhat more complicated than it actually is. If we could visualize six-dimensional geometry, we would see that yes, the fabric is tearing, but it does so in a fairly mild way. It's more like the handiwork of a moth on wool than that of a deep knee bend on shrunken trousers. Our work, and that of Witten, show that physical characteristics such as the number of families of string vibrations and the types of particles within each family are unaffected by these processes. As the Calabi-Yau space evolves through a tear, what can be affected are the precise values of the masses of the individual particles, the energies of the possible patterns of string vibrations. Our papers showed that these masses will vary continuously in response to the changing geometrical form of the Calabi-Yau component of space, some going up while others go down. Of primary importance, though, is the fact that there is no catastrophic jump, spike, or any unusual feature of these varying masses as the tear actually occurs. From the point of view of physics, the moment of tearing has no distinguishing characteristics. This point raises two issues. First, we have focused on tears in the spatial fabric that occur in the extra six-dimensional Calabi-Yau component of the universe. Can such tears also occur in the more familiar three extended spatial dimensions? The answer almost certainly is yes. After all, space is space, regardless of whether it is tightly curled up into a Calabi-Yau shape or is unfurled into the grand expanse of the universe we perceive on a clear, starry night. In fact, we have seen earlier that the familiar spatial dimensions might themselves actually be curled up into the form of a giant shape that curves back on itself way on the other side of the universe, and that therefore even the distinction between which dimensions are curled up and which are unfurled is somewhat artificial. Although our and Witten's analyses did rely on special mathematical features of Calabi-Yau shapes, the result, that the fabric of space can tear, is certainly of wider applicability. Second, could such a topology-changing tear happen today or tomorrow? Could it have happened in the past? Yes, experimental measurements of elementary particle masses show their values to be quite stable over time. But if we head back to the earliest epochs following the Big Bang, even non-string-based theories invoke important periods during which elementary particle masses do change over time. These periods, from a string-theoretic perspective, could certainly have involved the topology-changing tears discussed in this chapter. Closer to the present, the observed stability of elementary particle masses implies that if the universe is currently undergoing a topology-changing spatial tear, it must be doing it exceedingly slowly. So slowly that its effect on elementary particle masses is smaller than our present experimental sensitivity. Remarkably, so long as this condition is met, the universe could currently be in the midst of a spatial rupture. If it were occurring slowly enough, we would not even know it was happening. This is one of those rare instances in physics in which the seem to be unfortunate fundamental characteristics of string theory. But research since the mid-1990s has given us dramatic new hope that these features may be merely reflections of the way string theorists have been analyzing the theory. Briefly put, the equations of string theory are so complicated that no one knows their exact form. Physicists have managed to write down only approximate versions of the equations. It is these approximate equations that differ significantly from one string theory to the next. And it is these approximate equations, within the context of any one of the 5 string theories, that give rise to an abundance of solutions, a cornucopia of unwanted universes. Since 1990 Superstring Revolution. A summary of the second superstring revolution. The primary insight of the second superstring revolution is summarized by figures 12.1 and 12.2. In Figure 12.1, we see the situation prior to the recent ability to go, partially, beyond the approximation methods physicists have traditionally used to analyze string theory. We see that the 5 string theories were thought of as being completely separate. But with the newfound insights emerging from recent research, as indicated in Figure 12.2, we see that, like the starfish's 5 arms, all of the string theories are now viewed as a single, all-encompassing framework. In fact, by the end of this chapter we will see that even a 6th theory, a 6th arm, will be merged into this union. This overarching framework has provisionally been called M-theory, for reasons that will become clear as we proceed. Figure 12.2 represents a landmark achievement in the quest for the ultimate theory, till the seemingly disconnected threads of research in string theory have now been woven together into a single tapestry. A unique, all-encompassing theory that may well be the long-sought theory of everything. Although much work remains to be done, there are 2 essential features of M-theory that physicists have already uncovered. First, M-theory has 11 dimensions, 10 space and 1 time. Somewhat as Kaluza found that 1 additional spatial dimension allowed for an unexpected merger of general relativity and electromagnetism, string theorists have realized that 1 additional spatial dimension of the 1970s and 1980s that led to 1 time and 9 space dimensions was approximate, and that exact calculations, which can now be completed, show that 1 spatial dimension had hitherto been overlooked. The second feature of M-theory that has been discovered is that it contains vibrating strings, but it also includes other objects: vibrating 2-dimensional membranes, undulating 3-dimensional blobs, called 3 branes, and a host of other ingredients as well. As with the 11th dimension, this feature of M-theory emerges when calculations are freed from reliance on the approximations used prior to the mid-1990s. Beyond these, and a variety of other insights attained over the last few years, much of the true nature of M-theory remains mysterious. One suggested meaning for the M. Physicists worldwide are working with great vigor to acquire a full understanding of M-theory, and this may well constitute the central problem of 21st century physics. An approximation method. The limitations of the methods physicists have been using to analyze string theory are bound up with something called perturbation theory. Perturbation theory is an elaborate name for making an approximation to try to give a rough answer to a question, and then systematically improving this approximation by paying closer attention to fine details initially ignored. It plays an important part in many areas of scientific research, has been an essential element in understanding string theory, and, as we now illustrate, is also something we encounter frequently in our day-to-day lives. Imagine that one day your car is acting up, so you go see a mechanic to have it checked out. After giving your car a once-over, he gives you the bad news. The car needs a new engine block, for which parts and labor typically run in the $900 range. This is a ballpark approximation that you expect to be refined as the finer details of the work required become apparent. A few days later, having had time to run additional tests on the car, the mechanic gives you a more precise estimate, $950. He explains that you also need a new regulator, which with parts and labor costs about $50. Finally, when you go to pick up the car, he has added together all of the detailed contributions and presents you with a bill of $987.93. This, he explains, includes the $950 for the engine block and regulator, an additional $27 covering a fan belt, $10 for a battery cable, and 93 cents for an insulated bolt. The initial approximate figure of $900 has been refined by including more and more details. In physics terms, these details are referred to as perturbations to the initial estimate. When perturbation theory is properly and effectively applied, the initial estimate will be reasonably close to the final answer. When incorporated, the fine details ignored in the initial estimate make small differences in the final result. But sometimes when you go to pay a final bill, it is shockingly different from the initial estimate. Although you might use other, more emotive terms, technically this is called a failure of perturbation theory. This means that the initial approximation was not a good guide to the final answer because the refinements, rather than causing relatively small deviations, resulted in large changes to the ballpark estimate. As indicated briefly in earlier chapters, our discussion of string theory to this point has relied on a perturbative approach somewhat analogous to that used by the mechanic. The incomplete understanding of string theory that we have referred to from time to time has its roots, in one way or another, in this approximation method. Let's build up to an understanding of this important remark by discussing perturbation theory in a context that is less abstract than string theory, but closer to its string theory application than the example of the mechanic. A classical example of perturbation theory. Understanding the motion of the Earth through the solar system provides a classic example of using a perturbative approach. On such large distance scales, we need consider only the gravitational force. But unless further approximations are made, the equations encountered are extremely complicated. Remember that according to both Newton and Einstein, everything exerts a gravitational influence on everything else, and this quickly leads to a complex and mathematically intractable gravitational tug-of-war involving the Earth, the Sun, the Moon, the other planets, and, in principle, all other heavenly bodies as well. As you can imagine, it is impossible to take all of these influences into account and determine the exact motion of the Earth. In fact, even if there were only 3 heavenly participants, the equations become so complicated that no one has been able to solve them in full. Nevertheless, we can predict the motion of the Earth through the solar system with great accuracy by making use of a perturbative approach. The enormous mass of the Sun in comparison to that of every other member of our solar system and its proximity to the Earth in comparison to that of every other star makes it by far the dominant influence on the Earth's motion. And so, we can get a ballpark estimate by considering only the Sun's gravitational influence. For many purposes, this is perfectly adequate. If necessary, we can refine this approximation by sequentially including the gravitational effects of the next most relevant bodies, such as the Moon and whichever planets are passing closest by at the moment. The calculations can start to become difficult as the emerging web of gravitational influences gets complicated, but don't let this obscure the perturbative philosophy. The Sun-Earth gravitational interaction gives us an approximate explanation of the Earth's motion, while the remaining complex of other gravitational influences offers a sequence of ever smaller refinements. A perturbative approach works in this example because there is a dominant physical influence that admits a relatively simple theoretical description. This is not always the case. For example, if we are interested in the motion of 3 comparable mass stars orbiting one another in a trinary system, there is no single gravitational relationship whose influence dwarfs the others. Correspondingly, there is no single dominant interaction that provides a ballpark estimate, with the other effects yielding small refinements. If we tried to use a perturbative approach by, say, singling out the gravitational attraction between 2 stars and using it to determine our ballpark approximation, we would quickly find that our approach had failed. Our calculations would reveal that the refinement to the predicted motion arising from the inclusion of the 3rd star is not small, but in fact is as significant as the supposed ballpark approximation. This is familiar. The motion of 3 people dancing the hora bears little resemblance to 2 people dancing the tango. A large refinement means that the initial approximation was way off the mark, and the whole scheme was built on a house of cards. You should note that it is not simply a matter of including the large refinement due to the 3rd star. There is a domino effect. The large refinement has a significant impact on the motion of the other 2 stars, which in turn has a large impact on the motion of the 3rd star, which then has a substantial impact on the other 2, and so on. All strands in the gravitational web are equally important and must be dealt with simultaneously. Oftentimes, in such cases, our only recourse is to make use of the brute power of computers to simulate the resulting motion. This example highlights the importance, when using a perturbative approach, of determining whether the supposedly ballpark estimate really is in the ballpark, and if it is, which and how many of the finer details must be included in order to achieve a desired level of accuracy. As we now discuss, these issues are particularly crucial for applying perturbative tools to physical processes in the microworld. A perturbative approach to string theory. Physical processes in string theory are built up from the basic end of string loops, such as in Figure 6.7, which we reproduce in Figure 12.3 for convenience. String theorists have shown how a precise mathematical formula can be associated with the schematic portrayal of Figure 12.3, a formula that expresses the influence that each incoming string has on the resulting motion of the other. The details of the formula differ among the 5 string theories, but for the time being, we will ignore such subtle features. If it weren't for quantum mechanics, this formula would be the end of the story of how the strings interact. But the microscopic frenzy dictated by the uncertainty principle implies that string-anti-string pairs, 2 strings executing opposite vibrational patterns, can momentarily erupt into existence, borrowing energy from the universe, so long as they annihilate one another with sufficient haste, thereby repaying the energy loan. Such pairs of strings born of the quantum frenzy but which live on borrowed energy and hence must shortly recombine into a single loop are known as virtual string pairs. And even though it is only momentary, the transient presence of these additional virtual string pairs affects the detailed properties of the interaction. Those readers who skipped over the more precise answer section of Chapter 6 might find it helpful to skim the beginning part of that section. This is schematically depicted in Figure 12.4. The 2 initial strings slam together at the point marked A, where they merge together into a single loop. This loop travels a bit, but at B, frenzied quantum fluctuations result in the creation of a virtual string pair that travels along and then subsequently annihilates at C, producing, once again, a single string. Finally, at D, this string gives up its energy by dissociating into a pair of strings that head off in new directions. Because of the single loop in the center of Figure 12.4, physicists call this a one-loop process. As with the interaction depicted in Figure 12.3, a precise mathematical formula can be associated with this diagram to summarize the effect the virtual string pair has on the motion of the 2 original strings, but that's not the end of the story either, because quantum jitters can cause momentary virtual string eruptions to occur any number of times, producing a sequence of virtual string pairs. This gives rise to diagrams with more and more loops, as illustrated in the Figure 12.5. Each of these diagrams provides a handy and simple way of depicting the physical processes involved. The incoming strings merge together. Quantum jitters cause the resulting loop to split apart into a virtual string pair. These travel along and then annihilate one another by merging together into a single loop, which travels along and produces another virtual string pair, and on and on. As with the other diagrams, there is a corresponding mathematical formula for each of these processes that summarizes the effect on the motion of the original pair of strings. Moreover, just as the mechanic determined your final car repair bill through a refinement of his original estimate of $900 by adding to it $50, $27, $10.93, and just as we arrived at an ever more precise understanding of the motion of the Earth through a refinement of the Sun's influence, by including the smaller effects of the Moon and other planets, string theorists have shown that we can understand the interaction between 2 strings by adding together the mathematical expressions for diagrams with no loops, no virtual string pairs, with 1 loop, 1 pair of virtual strings odd with 2 loops, 2 pairs of virtual strings, and so forth, as illustrated in Figure 12.6. An exact calculation requires that we add together the mathematical expressions associated with each of these diagrams, with an increasingly large number of loops. But, since there are an infinite number of such diagrams and the mathematical calculations associated with each get increasingly difficult as the number of loops grows, this is an impossible task. Instead, string theorists have cast these calculations into a perturbative framework based on the expectation that a reasonable ballpark estimate is given by the zero-loop processes, with the loop diagrams resulting in refinements that get smaller as the number of loops increases. In fact, almost everything we know about string theory, including much of the material covered in previous chapters, has been discovered by physicists performing detailed and elaborate calculations using this perturbative approach. But to trust the accuracy of the results found, one must determine whether the supposedly ballpark approximations that ignore all but the first few diagrams in Figure 12.6 are really in the ballpark. This leads us to ask the crucial question: are we in the ballpark? Is the ballpark in the ballpark? It depends. Although the mathematical formula associated with each diagram becomes very complicated as the number of loops grows, string theorists have recognized one basic and essential feature. Somewhat as the strength of a rope determines the likelihood that vigorous pulling and shaking will cause it to tear into two pieces, there is a number that determines the likelihood that quantum fluctuations will cause a single string to split into two strings, momentarily yielding a virtual pair. This number is known as the string coupling constant. More precisely, each of the 5 string theories has its own string coupling constant, as we will discuss shortly. The name is quite descriptive. The size of the string coupling constant describes how strongly the quantum jitters of 3 strings, the initial loop and the 2 virtual loops into which it splits, are related, how tightly, so to speak, they are coupled to one another. The calculational formalism shows that the larger the string coupling constant, the more likely it is that quantum jitters will cause an initial string to split apart and subsequently rejoin. The smaller the string coupling constant, the less likely it is for such virtual strings to erupt momentarily into existence. We will shortly take up the question of determining the value of the string coupling constant within any of the 5 string theories. But first, what do we really mean by small or large when assessing its size? Well, the mathematics underlying string theory shows that the dividing line between small and large is the number 1 in the following sense. If the string coupling constant has a value less than 1, then, like multiple strikes of lightning, larger numbers of virtual string pairs are increasingly unlikely to erupt momentarily into existence. If the coupling constant is 1 or greater, however, it is increasingly likely that ever larger numbers of such virtual pairs will momentarily burst on the scene. The upshot is that if the string coupling constant is less than 1, the loop diagram contributions become ever smaller as the number of loops grows. This is just what is needed for the perturbative framework, since it indicates that we will get reasonably accurate results even if we ignore all processes except for those with just a few loops. But if the string coupling constant is not less than 1, the loop diagram contributions become more important as the number of loops increases. As in the case of a trinary star system, this invalidates a perturbative approach. The supposed ballpark approximation, the process with no loops, is not in the ballpark. This discussion applies equally well to each of the 5 string theories, with the value of the string coupling constant in any given theory determining the efficacy of the perturbative approximation scheme. This realization leads us to the next crucial question. What is the value of the string coupling constant? Or more precisely, what are the values of the string coupling constants in each of the 5 string theories? At present, no one has been able to answer this question. It is one of the most important unresolved issues in string theory. We can be sure that conclusions based on a perturbative framework are justified only if the string coupling constant is less than 1. Moreover, the precise value of the string coupling constant has a direct impact on the masses and charges carried by the various string vibrational patterns. Thus we see that much of physics hinges on the value of the string coupling constant. And so, let's take a closer look at why the important question of its value, in any of the 5 string theories, remains unanswered. The equations of string theory. The perturbative approach for determining how strings interact with one another can also be used to determine the fundamental equations of string theory. In essence, the equations of string theory determine how strings interact and, conversely, the way strings interact directly determine the equations of the theory. As a prime example, in each of the 5 string theories there is an equation that is meant to determine the value of the theory's coupling constant. Currently, however, physicists have been able to find only an approximation to this equation, in each of the 5 string theories, by mathematically evaluating a small number of relevant string diagrams using a perturbative approach. Here is what the approximate equations say. In any of the 5 string theories, the string coupling constant takes on a value such that if it is multiplied by 0, the result is 0. This is a terribly disappointing equation. Since any number times 0 yields 0, the equation can be solved with any value of the string coupling constant. Thus, in any of the 5 string theories, the approximate equation for its string coupling constant gives us no information about its value. While we are at it, In each of the 5 string theories, there is another equation that is supposed to determine the precise form of both the extended and the curled-up spacetime dimensions. The approximate version of this equation that we currently have is far more restrictive than the one dealing with the string coupling constant, but it still admits many solutions. For instance, 4 extended spacetime dimensions together with any curled-up, 6-dimensional Calabi-Yau space provide a whole class of solutions. But even this does not exhaust the possibilities, which also allow for a different split between the number of extended and curled-up dimensions. What can we make of these results? There are 3 possibilities. First, starting with the most pessimistic possibility, although each string theory comes equipped with equations to determine the value of its coupling constant as well as the dimensionality and precise geometrical form of spacetime, something no other theory can claim. Even the as-yet unknown exact form of these equations may admit a vast spectrum of solutions, substantially weakening their predictive power. If true, this would be a setback, since the promise of string theory is that it will be able to explain these features of the cosmos rather than require us to determine them from experimental observation and, more or less arbitrarily, insert them into the theory. We will return to this possibility in Chapter 15. Second, the unwanted flexibility in the approximate string equations may be an indication of a subtle flaw in our reasoning. We are attempting to use a perturbative approach to determine the value of the string coupling constant itself. But, as discussed, perturbative methods are sensible only if the coupling constant is less than 1, and hence our calculation may be making an unjustified assumption about its own answer, namely that the result will be smaller than 1. Our failure could well indicate that this assumption is wrong and that perhaps the coupling in any one of the 5 string theories is greater than 1. Third, the unwanted flexibility may merely be due to our use of approximate rather than exact equations. For instance, even though the coupling constant in a given string theory might be less than 1, the equations of the theory may still depend sensitively on the contributions from all diagrams. That is, the accumulated small refinements from diagrams with ever more loops might be essential for modifying the approximate equations, which admit many solutions, into exact equations that are far more restrictive. By the early 1990s, the latter 2 possibilities made it clear to most string theorists that complete reliance on the perturbative framework was standing squarely in the way of progress. The next breakthrough, most everyone in the field agreed, would require a non-perturbative approach, an approach that was not shackled to approximate calculational techniques and could therefore reach well beyond the limitations of the perturbative framework. As of 1994, finding such a means seemed like a pipe dream. Sometimes, though, pipe dreams spill over into reality. Duality. Hundreds of strangely has never seen ice. Through a chance meeting, they decide to team up for a camping trip in the desert. When they set out to leave, each is fascinated by the other's gear. The ice lover is captivated by the water lover's silky, smooth, transparent liquid, and the water lover is strangely drawn to the remarkable solid crystal cubes brought by the ice lover. Neither has any inkling that there is actually a deep relationship between water and ice. To them, they are 2 completely different substances. But as they head out into the scorching heat of the desert, they are shocked to find that the ice slowly begins to turn into water. And, in the frigid cold of the desert night, they are equally shocked to find that the liquid water slowly begins to turn into solid ice. They realize that these 2 substances, which they initially thought to be completely unrelated, are intimately connected. The duality among the 5 string theories is somewhat similar. Roughly speaking, the string coupling constants play a role analogous to temperature in our desert analogy. Like ice and water, any 2 of the 5 string theories at first sight appear to be completely distinct, but as we vary their respective coupling constants, the theories transmute among themselves. Just as ice transmutes into water as we raise its temperature, one string theory can transmute into another as we increase the value of its coupling constant. This takes us a long way toward showing that all of the string theories are dual descriptions of one single underlying structure, the analog of H2O for water and ice. The reasoning underlying these results relies almost entirely on the use of arguments rooted in principles of symmetry. Let's discuss this. The power of symmetry. Over the years, no one even attempted to study the properties of any of the 5 string theories for large values of their string coupling constants because no one had any idea how to proceed without the perturbative framework. However, during the late 1980s and early 1990s, physicists made slow but steady progress in identifying certain special properties, including certain masses and force charges, that are part of the strong coupling physics of a given string theory, and yet are still within our ability to calculate. The calculation of these properties, which necessarily transcends the perturbative framework, has played a central role in driving the progress of the second superstring revolution, and is firmly rooted in the power of symmetry. Symmetry principles provide insightful tools for understanding a great many things about the physical world. We have discussed, for instance, that the well-supported belief that the laws of physics do not treat any place in the universe or moment in time as special allows us to argue that the laws governing the here and now are the same ones at work everywhere and every when. This is a grandiose example, but symmetry principles can be equally important in less all-encompassing circumstances. For instance, if you witness a crime but were able to catch only a glimpse of the right side of the perpetrator's face, a police artist can nonetheless use your information to sketch the whole face. Symmetry is why. Although there are differences between the left and right sides of a person's face, most are symmetric enough that an image of one side can be flipped over to get a good approximation of the other. In each of these widely different applications, the power of symmetry is its ability to nail down properties in an indirect manner, something that is often far easier than a more direct approach. We could learn about fundamental physics in the Andromeda Galaxy by going there, finding a planet around some star, building accelerators, and performing the kinds of experiments carried out on Earth. But the indirect approach of invoking symmetry under changes of locale is far easier. We could also learn about features on the left side of the perpetrator's face by tracking him down and examining it. But it is often far easier to invoke the left-right symmetry of faces. Supersymmetry is a more abstract symmetry principle that relates physical properties of elementary constituents that carry different amounts of spin. At best, there are only hints from experimental results that the microworld incorporates this symmetry. But, for reasons discussed earlier, there is a strong belief that it does. It is certainly an integral part of string theory. In the 1990s, led by the pioneering work of Nathan Seberg of the Institute for Advanced Study, physicists have realized that supersymmetry provides a sharp and incisive tool that can answer some very difficult and important questions by indirect means. Even without understanding intricate details of a theory, the fact that it has supersymmetry built in allows us to place significant constraints on the properties it can have. Using a linguistic analogy, imagine that we are told that a sequence of letters has been written on a slip of paper, that the sequence has exactly 3 occurrences, say of the letter Y, thus give us a tangible grip on some of its strong coupling characteristics. As the coupling constant in a chosen string theory is increased beyond the realm accessible to perturbation theory, we anchor our limited understanding in the BPS states. Like a few choice words in a foreign tongue, we will find that they will take us quite far. Duality in string theory. Following Witten, let's start with one of the 5 string theories, say the type 1 string, and imagine that all of its 9 space dimensions are flat and unfurled. This, of course, is not at all realistic, but it makes the discussion simpler. We will return to curled-up dimensions shortly. We begin by assuming that the string coupling constant is much less than 1. In this case, perturbative tools are valid, and hence many of the detailed properties of the theory can and have been worked out with accuracy. If we increase the value of the coupling constant but still keep it a good deal less than 1, perturbative methods can still be used. The detailed properties of the theory will change somewhat. For instance, the numerical values associated with the scattering of one string off another will be a bit different because the multiple loop processes of figure 12.6 make greater contributions when the coupling constant increases. But beyond these changes in detailed numerical properties, the overall physical content of the theory remains the same, so long as the coupling constant stays in the perturbative realm. As we increase the type 1 string coupling constant beyond the value 1, perturbative methods become invalid, and so we focus only on the limited set of non-perturbative masses and charges, the BPS states, that are still within our ability to understand. Here is what Witten argued and later confirmed through joint work with Joe Polchinski of the University of California at Santa Barbara. These strong coupling characteristics of type 1 string theory exactly agree with known properties of heterotic O string theory, when the latter has a small value for its string coupling constant. That is, when the coupling constant of the type 1 string is large, the particular masses and charges that we know how to extract are precisely equal to those of the heterotic O string when its coupling constant is small. This gives us a strong indication that these two string theories, which at first sight, like water and ice, seem totally different, are actually dual. It persuasively suggests that the physics of the type 1 theory for large values of its coupling constant is identical to the physics of the heterotic O theory for small values of its coupling constant. Related arguments gave equally persuasive evidence that the reverse is also true, the physics of the type. When a theory for small values of its coupling constant is identical to that of the heterotic O theory for large values of its coupling constant. Although the two string theories appear to be unrelated when analyzed using the perturbative approximation scheme, we now see that each transforms into the other, somewhat like the transmutation between water and ice, as their coupling constants are varied in value. This central new kind of result, in which the strong coupling physics of one theory is described by the weak coupling physics of another theory, is known as strong-weak duality. As with the other dualities discussed previously, it tells us that the two theories involved are not actually distinct. Rather, they give two dissimilar descriptions of the same underlying theory. Unlike the English-Chinese trivial duality, strong-weak coupling duality is powerful. When the coupling constant of one member of a dual pair of theories is small, we can analyze its physical properties using well-developed perturbative tools. If the coupling constant of the theory is large, however, and thus the perturbative methods break down, we now know that we can use the dual description, a description in which the relevant coupling constant is small, and return to the use of perturbative tools. The translation has resulted in our having quantitative methods to analyze a theory we initially thought to be beyond our theoretical abilities, actually proving that the strong coupling physics of the type 1 string theory is identical to the weak coupling physics of the heterotic O theory, and vice versa, is an extremely difficult task that has not yet been achieved. The reason is simple. One member of the pair of the supposedly dual theories is not amenable to perturbative analysis as its coupling constant is too big. This prevents direct calculations of many of its physical properties. In fact, it is precisely this point that makes the proposed duality so potent, for if true, it provides a new tool for analyzing a strongly coupled theory. Use perturbative methods on its weakly coupled dual description. But even if we cannot prove that the two theories are dual, the perfect alignment between those properties we can extract with confidence provides extremely compelling evidence that the conjectured strong-weak coupling relationship between the type 1 and heterotic O string theories is correct. In fact, increasingly clever calculations that have been performed to test the proposed duality have all resulted in positive results. Most string theorists are convinced that the duality is true. Following the same approach, one can study the strong coupling properties of another of the remaining string theories, say the type 2b string. As originally conjectured by Hull and Townsend and supported by the research of a number of physicists, something equally remarkable appears to occur. As the coupling constant of the type 2b string gets larger and larger, the physical properties that we are still able to understand appear to match up exactly with that of the weakly coupled type 2b string itself. In other words, the type 2b string is self-dual. Specifically, detailed analysis persuasively suggests that if the type 2b coupling constant were larger than 1, and if we were to change its value to its reciprocal, whose value therefore is less than 1, the resulting theory is absolutely identical to the one we started with. Similar to what we found in trying to squeeze a circular dimension to a sub-Planck scale length, if we try to increase the type 2b coupling to a value larger than 1, The self-duality shows that the resulting theory is precisely equivalent to the type 2b string with a coupling smaller than 1. A summary so far. Let's see where we are. By the mid-1980s, physicists had constructed 5 different superstring theories. In the approximation scheme of perturbation theory, they all appear to be distinct, but this approximation method is valid only if the string coupling constant in a given string theory is less than 1. The expectation has been that physicists should be able to calculate the precise value of the string coupling constant in any given string theory, but the form of the approximate equations currently available makes this impossible. For this reason, physicists aim to study each of the 5 string theories for a range of possible values of their respective coupling constants, both less than and greater than 1. That is, both weak and strong coupling. But traditional perturbative methods give no insight into the strong coupling characteristics of any of the string theories. Recently, by making use of the power of supersymmetry, physicists have learned how to calculate some of the strong coupling properties of a given string theory. And to the surprise of most everyone in the field, the strong coupling properties of the heterotic O string appear to be identical to the weak coupling properties of the type 1 string, and vice versa. Moreover, the strong coupling physics of the type 2b string is identical to its own properties when its coupling is weak. These unexpected links encourage us to follow Witten and press on to the other 2 string theories, type 2OA and heterotic E, to see how they fit into the overall picture. Here we will find even more exotic surprises. To prepare ourselves, we need a brief historical digression. Supergravity. In the late 1970s and early 1980s, before the surge of interest in string theory, many theoretical physicists sought a unified theory of quantum mechanics, gravity, and the other forces in the framework of point-particle quantum field theory. The hope was that the inconsistencies between point-particle theories involving gravity and quantum mechanics would be overcome by studying theories with a great deal of symmetry. In 1976, Daniel Friedman, Sergio Ferrara, and Peter van Nieuwenhuizen, all then of the State University of New York at Stony Brook, discovered that the most promising were those involving supersymmetry, since the tendency of bosons and fermions to give canceling quantum fluctuations helps to calm the violent microscopic frenzy. The authors coined the term supergravity to describe supersymmetric quantum field theories that try to incorporate general relativity. Such attempts to merge general relativity with quantum mechanics ultimately met with failure. Nevertheless, as mentioned in Chapter 8, there was a prescient lesson to be learned from these investigations, one that presaged the development of string theory. The lesson, which perhaps became most clear through the work of Eugene Kremer, Bernard Julia, and Scherk, all of the École Normale Supérieure in 1978, was that the attempts that came closest to success were supergravity theories formulated not in 4 dimensions, but in more. Specifically, the most promising were the versions calling for 10 or 11 dimensions, with 11 dimensions, it turns out, being the maximal possible. Contact with 4 observed dimensions was accomplished in the framework, once again, of Kaluza and Klein. The extra dimensions were curled up. In the 10-dimensional theories, as in string theory, 6 dimensions were curled up, while 7 were curled up for the 11-dimensional theory. When string theory took physicists by storm in 1984, the perspective on point-particle supergravity theories changed dramatically. As emphasized repeatedly, if we examine a string with the precision available currently and for the foreseeable future, it looks like a point particle. We can make this informal remark precise. When studying low-energy processes in string theory, those processes that do not have enough energy to probe the ultra-microscopic extended nature of the string, we can approximate a string by a structureless point particle using the framework of point-particle quantum field theory. We cannot use this approximation when dealing with the short-distance or high-energy processes because we know that the extended nature of the string is crucial to its ability to resolve the conflicts between general relativity and quantum mechanics that a point-particle theory cannot. But at low enough energies, large enough distances, these problems are not encountered, and such an approximation is often made for the sake of calculational convenience. The quantum field theory that most closely approximates string theory in this manner is none other than 10-dimensional supergravity. The special properties of 10-dimensional supergravity discovered in the 1970s and 1980s are now understood to be low-energy relics of the underlying power of string theory. Researchers studying 10-dimensional supergravity had uncovered the tip of a very deep iceberg. The rich structure of superstring theory, in fact, it turns out that there are 4 different 10-dimensional supergravity theories that differ in details regarding the precise way in which supersymmetry is incorporated. 3 of these turn out to be the low-energy point-particle approximations to the type 2A string, the type 2B string, and the heterotic E string. The 4th gives the low-energy point-particle approximation to both the type 1 string and the heterotic O string. In retrospect, this was the first indication of the close connection between these 2 string theories. This is a very tidy story, except that 11-dimensional supergravity seems to have been left out in the cold. String theory, formulated in 10 dimensions, appears to have no room for an 11-dimensional theory. For a number of years, the general view held by most but not all string theorists was that 11-dimensional supergravity was a mathematical oddity without any connection to the physics of string theory, glimmers of M theory. The view now is very different. At Strings 95, Witten argued that if we start with the type 2OA string and increase its coupling constant from a value much less than 1 to a value much greater than 1, the physics we are still able to analyze, essentially that of the BPS-saturated configurations, has a low-energy approximation that is 11-dimensional supergravity. When Witten announced this discovery, it stunned the audience, and it has since rocked the string theory community. For almost everyone in the field, it was a completely unexpected development. Your first reaction to this result may echo that of most experts in the field. How can a theory specific to 11 dimensions be relevant to a different theory in 10? The answer is of deep significance. To understand it, we must describe Witten's result more precisely. Actually, it's easier first to illustrate a closely related result discovered later by Witten and a postdoctoral fellow at Princeton University, Peter Harava, that focuses on the heterotic E string. They found that the strongly coupled heterotic E string also has an 11-dimensional description, and Figure 12.7 shows why. In the leftmost part of the figure, we take the heterotic E string coupling constant to be much smaller than 1. This is the realm that we have been describing in previous chapters and that string theorists have studied for well over a decade. As we move to the right in Figure 1.2.7, we sequentially increase the size of the coupling constant. Prior to 1995, string theorists knew that this would make the loop processes, see Figure 12.6, increasingly important and, as the coupling constant got larger, would ultimately invalidate the whole perturbative framework. But what no one suspected is that as the coupling constant is made larger, a new dimension becomes visible. This is the vertical dimension shown in Figure 12.7. Bear in mind that in this figure the two-dimensional grid with which we begin represents all 9 spatial dimensions of the heterotic E string. Thus, the new vertical dimension represents a 10th spatial dimension, which, together with time, takes us to a total of 11 space-time dimensions. Moreover, Figure 12.7 illustrates a profound consequence of this new dimension. The structure of the heterotic E string changes as this dimension grows. It is stretched from a one-dimensional loop into a ribbon, and then a deformed cylinder as we increase the size of the coupling constant. In other words, the heterotic E string is actually a two-dimensional membrane whose width, the vertical extent in Figure 12.7, is controlled by the size of the coupling constant. For over a decade, string theorists have always used perturbative methods that are firmly rooted in the assumption that the coupling constant is very small. As argued by Witten, this assumption has made the fundamental ingredients look and behave like one-dimensional strings, even though they actually have a hidden second spatial dimension. By relaxing the assumption that the coupling constant is very small and considering the physics of the heterotic E string when the coupling constant is large, the second dimension becomes manifest. This realization does not invalidate any of the conclusions we have drawn in previous chapters, but it does force us to see them within a new framework. For instance, How does this all mesh with the 1 time and 9 space dimensions required by string theory? Well, recall from Chapter 8 that this constraint arises from counting the number of independent directions in which a string can vibrate, and requiring that this number be just right to ensure that quantum mechanical probabilities have sensible values. The new dimension we have just uncovered is not one in which a heterotic E string can vibrate, since it is a dimension that is locked within the structure of the strings themselves. Put another way, the perturbative framework that physicists used in deriving the requirement of a 10-dimensional spacetime assumed from the outset that the heterotic E coupling constant is small. Although it was not recognized until much later, this implicitly enforced two mutually consistent approximations: that the width of the membrane in the figure 12.7 is small, making it look like a string, and that the 11th dimension is so small that it is beyond the sensitivity of the perturbative equations. Within this approximation scheme, we are led to envision a 10-dimensional universe filled with one-dimensional strings. Now we see that this is but an approximation to an 11-dimensional universe containing two-dimensional membranes. For technical reasons, Witten first came upon the 11th dimension in his studies of the strong coupling properties of the type 1 Ia string, and there the story is quite similar. As in the heterotic E example, there is an 11th dimension whose size is controlled by the type 2Ia coupling constant. When its value is increased, the new dimension grows. As it does, Witten argued, the type 2A string, rather than stretching into a ribbon as in the heterotic E case, expands into an inner tube, as illustrated in figure 12.8. Once again, Witten argued that although theorists have always viewed type 2A strings as one-dimensional objects, having only length but no thickness, this view is a reflection of the perturbative approximation scheme in which the string coupling constant is assumed to be small. If nature does require a small value of this coupling constant, then it is a trustworthy approximation. Nevertheless, Witten's arguments and those of other physicists during the second superstring revolution do give strong evidence that the type 1A and heterotic E strings are, fundamentally, two-dimensional membranes living in an 11-dimensional universe. But what is this 11-dimensional theory? At low energies, low compared to the Planck energy, Witten and others argued, it is approximated by the long-neglected 11-dimensional supergravity quantum field theory. But for higher energies, how can we describe this theory? This topic is currently under intense scrutiny. We know from figures 12.7 and 12.8 that the 11-dimensional theory contains two-dimensional extended objects, two-dimensional membranes, and as we shall soon discuss, extended objects of other dimensions play an important role as well. But beyond a hodgepodge of properties, no one knows what this 11-dimensional theory is. Are membranes its fundamental ingredients? What are its defining properties? How does it purport to make contact with physics as we know it? If the respective coupling constants are small, our best current answers to these questions are described in previous chapters. Since at small coupling constants we are led back to the theory of strings. But if the coupling constants are not small, no one currently knows the answers. Whatever the 11-dimensional theory is, Witten has provisionally named it M-theory. The name stands for as many things as people you poll. Some samples: mystery theory, mother theory, as in mother of all theories, membrane theory, since whatever it is, membranes seem to be part of the story, matrix theory, after some recent work by Tom Banks of Rutgers University, Willie Fischler of the University of Texas at Austin, Stephen Schenker of Rutgers University, and Susskind that offers a novel interpretation of the theory. But even without having a firm grasp on its name or its properties, it is already clear that M-theory provides a unifying substrate for pulling together all 5 string theories, M-theory and the web of interconnections. There is an old proverb about 3 blind men and an elephant. The first blind man grabs hold of the elephant's ivory tusk and describes the smooth, hard surface that he feels. The second blind man grabs hold of one of the elephant's legs. He describes the tough, muscular girth that he feels. The third blind man grabs hold of the elephant's tail and describes the slender and sinewy appendage that he feels. Since their mutual descriptions are so different, and since none of the men can see the others, each thinks that he has grabbed hold of a different animal. For many years, physicists were as much in the dark as the blind men, thinking that the different string theories were very different. But now, through the insights of the second superstring revolution, physicists have realized that M theory is the unifying pachyderm of the 5 string theories. In this chapter, we have discussed changes in our understanding of string theory that arise when we venture beyond the domain of the perturbative framework, a framework implicitly in use prior to this chapter. Figure 12.9 summarizes the interrelations we have found so far, with arrows to indicate dual theories. As you can see, we have a web of connections, but it is not yet complete. By also including the dualities of Chapter 10, we can finish the job. Recall the large-small circular radius duality that interchanges a circular dimension of radius r with one whose radius is 1r. Previously, we glossed over one aspect of this duality which we now must clarify. In Chapter 10, we discussed the properties of strings in a universe with a circular dimension without carefully specifying which of the 5 string formulations we were working with. We argued that the interchange of winding and vibration modes of a string allows us to rephrase exactly the string theoretic description of a universe with a circular dimension of radius 1r in terms of one in which the radius is r. The point we glossed over is that the type 2a and type 2b string theories actually get exchanged by this duality, as do the heterotic O and heterotic E strings. That is, the more precise statement of the large-small radius duality is this. The physics of the type Yatsu-Ui-A string in a universe with a circular dimension of radius r is absolutely identical to the physics of the type 22b string in a universe with a circular dimension of radius 1/r. A similar statement holds for the heterotic E and heterotic O strings. This refinement of the large-small radius duality has no significant effect on the conclusions of Chapter 10, but it does have an important impact on the present discussion. The reason is that by providing a link between the type 2a and type 2b string theories, as well as between the heterotic O and heterotic E theories, the large-small radius duality completes the web of connections, as illustrated by the dotted lines in Figure 12.10. This figure shows that all 5 string theories, together with M theory, are dual to one another. They are all sewn together into a single theoretical framework. They provide 5 different approaches to describing one and the same underlying physics. For some or other application, one phrasing may be far more effective than another. For instance, it's far easier to work with the weakly coupled heterotic O theory than it is to work with the strongly coupled type 1 string. Nevertheless, they describe exactly the same physics, the overall picture. We can now more fully understand the 2 figures, figures 12.1 and 12.2, that we introduced in the beginning of this chapter to summarize the essential points. In Figure 12.1, we see that prior to 1995, without taking any dualities into account, we had 5 apparently distinct string theories. Various physicists worked on each, but without an understanding of the dualities, they appeared to be different theories. Each of the theories had variable features such as the size of their coupling constant and the geometrical form and sizes of curled-up dimensions. The hope was, and still is, that these defining properties would be determined by the theory itself, but without the ability to determine them with the current approximate equations, physicists have naturally studied the physics that follows from a range of possibilities. This is represented in Figure 12.1 by the shaded regions. Each point in such a region denotes one specific choice for the coupling constant and the curled-up geometry. Without invoking any dualities, we still have 5 disjointed collections of theories. But now, if we apply all of the dualities we have discussed, then, as we vary the coupling and geometric parameters, we can pass from any one theory to any other, so long as we also include the unifying central region of M theory. Even though we have only a scant understanding of M theory, these indirect arguments lend strong support to the claim that it provides a unifying substrate for our 5 naively distinct string theories. Moreover, we have learned that M-theory is closely related to yet a sixth theory, 11-dimensional supergravity, and this is recorded in Figure 12.11, a more precise version of Figure 12.2. Figure 12.11 illustrates that the fundamental ideas and equations of M-theory, although only partially understood at the moment, unify those of all of the formulations of string theory. M-theory is the theoretical elephant that has opened the eyes of string theorists to a far grander unifying framework. A surprising feature of M-theory: democracy in extension. When the string coupling constant is small in any of the upper 5 peninsular regions of the theory map in Figure 12.11, the fundamental ingredient of the theory appears to be a one-dimensional string. We have, however, just gained a new perspective on this observation. If we start in either the heterotic E or type 2A regions and turn the value of the respective string coupling constants up, we migrate toward the center of the map in Figure 12.11, and what appeared to be one-dimensional strings stretch into two-dimensional membranes. Moreover, through a more or less intricate sequence of duality relations involving both the string coupling constants and the detailed form of the curled-up spatial dimensions, we can smoothly and continuously move from any point in Figure 12.11 to any other. Since the two-dimensional membranes we have come upon from the heterotic E and type 2A perspectives can be followed as we migrate to any of the three other string formulations in Figure 12.11, we learn that each of the 5 string formulations involves two-dimensional membranes as well. This raises two questions. First, are two-dimensional membranes the true fundamental ingredient of string theory? And second, having made the bold leap in the 1970s and early 1980s from zero-dimensional point particles to one-dimensional strings, and having now seen that string theory actually involves two-dimensional membranes, might it be that there are even higher-dimensional ingredients in the theory as well? As of this writing, the answers to these questions are not fully known, but the situation appears to be the following. We relied heavily on supersymmetry to give us some understanding of each formulation of string theory beyond the domain of validity of perturbative approximation methods. In particular, the properties of BPS states, their masses, and their force charges are uniquely determined by supersymmetry, and this allowed us to understand some of their strongly coupled characteristics without having to perform direct calculations of unimaginable difficulty. In fact, through the initial efforts of Horowitz and Strominger, and through subsequent groundbreaking work of Polchinski, we now know even more about these BPS states. In particular, not only do we know their masses and the force charges they carry, but we also have a clear understanding of what they look like. And the picture is perhaps the most surprising development of all. Some of the BPS states are one-dimensional strings. Others are two-dimensional membranes. By now, these shapes are familiar, but the surprise is that yet others are three-dimensional, four-dimensional. In fact, the range of possibilities encompasses every spatial dimension up to and including 9. String theory, or M-theory, or whatever it is finally called, actually contains extended objects of a whole slew of different spatial dimensions. Physicists have coined the term three-brane to describe extended objects with 3 spatial dimensions, 4-brane for those with 4 spatial dimensions, and so on up to 9 branes, and more generally, for an object with p space dimensions, where p represents a whole number, physicists have coined the far from euphonious terminology p-brane. Sometimes, using this terminology, strings are described as 1-branes and membranes as 2-branes. The fact that all of these extended objects are actually part of the theory has led Paul Townsend to declare a democracy of branes. Notwithstanding brane democracy, strings, one-dimensional extended objects, are special for the following reason. Physicists have shown that the mass of the extended objects of every dimension except for one-dimensional strings is inversely proportional to the value of the associated string coupling constant when we are in any of the 5 string regions of Figure 12.11. This means that with weak string coupling in any of the 5 formulations, all but the strings will be enormously massive, orders of magnitude heavier than the Planck mass. Because they are so heavy, and therefore from E equals sine mc2, require such unimaginably high energy to be produced, brains have only a small effect on much of physics, but not on all, as we shall see in the next chapter. However, when we venture outside the peninsular regions of Figure 12.11, the higher dimensional brains become lighter and hence increasingly important. And so, the image you should have in mind is the following. In the central region of Figure 12.11, we have a theory whose fundamental ingredients are not just strings or membranes, but rather brains of a variety of dimensions, all more or less on equal footing. Currently, we do not have a firm grasp on many essential features of this full theory. But one thing we do know is that as we move from the central region to any of the peninsular regions, only the strings, or membranes curled up to look ever more like strings, as in figures 12.7 and 12.8, are light enough to make contact with physics as we know it, the particles of Table 1.1, and the four forces through which they interact. The perturbative analyses string theorists have made use of for close to 2 decades have not been refined enough to discover even the existence of the supermassive extended objects of other dimensions. Strings dominated the analyses, and the theory was given the far from democratic name of string theory. Again, in these regions of Figure 12.11, we are justified, for most considerations, in ignoring all but the strings. In essence, this is what we have done so far in this book. We see now, though, that in actuality the theory is more rich than anyone previously imagined. Does any of this solve the unanswered questions in string theory? Yes and no. We have managed to deepen our understanding by breaking free of certain conclusions that, in retrospect, were a consequence of perturbative, approximate analyses rather than true string physics. But the current scope of our non-perturbative tools is quite limited. The discovery of the remarkable web of duality relations affords us far greater insight into string theory, but many issues remain unresolved. At present, for example, we do not know how to go beyond the approximate equations for the value of the string coupling constant, equations that, as we have seen, are too coarse to give us any useful information, nor do we have any greater insight into why there are precisely 3 extended spatial dimensions, or how to choose the detailed form for the curled-up dimensions. These questions require more sharply honed non-perturbative methods than we currently possess. What we do have is a far deeper understanding of the logical structure and theoretical reach of string theory. Prior to the realizations summarized in Figure 12.11, the strong coupling behavior of each string theory was a black box, a complete mystery. As on maps of old, the realm of strong coupling was uncharted territory, potentially filled with dragons and sea monsters. But now we see that although the journey to strong coupling may take us through unfamiliar regions of M theory, it ultimately lands us back in the comfortable surrounds of weak coupling, albeit in the dual language of what was once thought to be a different string theory. Duality and M theory unite the 5 string theories, and they suggest an important conclusion. It may well be that there aren't other surprises, on par with the ones just discussed, that are awaiting our discovery. Once a cartographer can fill in every region on a spherical globe of the Earth, the map is done, and geographical knowledge is complete. That's not to say explorations in Antarctica or on an isolated island in Micronesia are without scientific or cultural merit. It only means that the age of geographic discovery is over. The absence of blank spots on the globe ensures this. The theory map of Figure 12.11 plays a similar role for string theorists. It covers the entire range of theories that can be reached by setting sail from any one of the 5 string constructions. Although we are far from a full understanding of the terra incognita of M theory, there are no blank regions on the map. Like the cartographer, the string theorist can now claim with guarded optimism that the spectrum of logically sound theories incorporating the essential discoveries of the past century. Special and general relativity, quantum mechanics, gauge theories of the strong, weak, and electromagnetic forces, supersymmetry, extra dimensions of Kaluza and Klein is fully mapped out by Figure 12.11. The challenge to the string theorist, or perhaps we should say the M theorist, is to show that some point on the theory map of Figure 12.11 actually describes our universe. To do this requires finding the full and exact equations whose solution will pick out this elusive point on the map, and then understanding the corresponding physics with sufficient precision to allow comparisons with experiment. As Witten has said, understanding what M-theory really is, the physics it embodies, would transform our understanding of nature at least as radically as occurred in any of the major scientific upheavals of the past. This is the program for unification in the 21st century. Chapter 13. Black Holes, a String / M-Theory. Perspective. The pre-string theory, conflict between general relativity and quantum mechanics, was an affront to our visceral sense that the laws of nature should fit together in a seamless, coherent whole. But this antagonism was more than a towering abstract disjunction. The extreme physical conditions that occurred at the moment of the Big Bang and that prevail within black holes cannot be understood without a quantum mechanical formulation of the gravitational force. With the discovery of string theory, we now have a hope of solving these deep mysteries. In this and the next chapter, we describe how far string theorists have gone toward understanding black holes and the origin of the universe. Black holes and elementary particles. At first sight, it's hard to imagine any two things more radically different than black holes and elementary particles. We usually picture black holes as the most gargantuan of heavenly bodies, whereas elementary particles are the most minute specks of matter. But the research of a number of physicists during the late 1960s and early 1970s, including Dimitrios Christodoulou, Werner Israel, Richard Price, Brandon Carter, Roy Kerr, David Robinson, Hawking, and Penrose, showed that black holes and elementary particles are perhaps not as different as one might think. These physicists found increasingly persuasive evidence for what John Wheeler has summarized by the statement, "Black holes have no hair." By this, Wheeler meant that, except for a small number of distinguishing features, all black holes appear to be alike. The distinguishing features? One, of course, is the black hole's mass. What are the others? Research has revealed that they are the electric and certain other force charges a black hole can carry, as well as the rate at which it spins. And that's it. Any two black holes with the same mass, force charges, and spin are completely identical. Black holes do not have fancy hairdos, that is, other intrinsic traits, that distinguish one from another. This should ring a loud bell. Recall that it is precisely such properties, mass, force charges, and spin, that distinguish one elementary particle from another. The similarity of the defining traits has led a number of physicists over the years to the strange speculation that black holes might actually be gigantic elementary particles. In fact, according to Einstein's theory, there is no minimum mass for a black hole. If we crush a chunk of matter of any mass to a small enough size, a straightforward application of general relativity shows that it will become a black hole. The lighter the mass, the smaller we must crush it. And so, we can imagine a thought experiment in which we start with ever lighter blobs of matter, crush them into ever smaller black holes, and compare the properties of the resulting black holes with the properties of elementary particles. Wheeler's no-hair statement leads us to conclude that for small enough masses, the black holes we form in this manner will look very much like elementary particles. Both will look like tiny bundles characterized completely by their mass, force charges, and spin. But there is a catch. Astrophysical black holes with masses many times that of the Sun are so large and heavy that quantum mechanics is largely irrelevant, and only the equations of general relativity need be used to understand their properties. We are here discussing the overall structure of the black hole, not the singular central point of collapse within a black hole, whose tiny size most certainly requires a quantum mechanical description. As we try to make ever less massive black holes, however, there comes a point when they are so light and small that quantum mechanics comes into play. This happens if the total mass of the black hole is about the Planck mass or less. From the point of view of elementary particle physics, the Planck mass is huge, some 10 billion times the mass of a proton. From the point of view of black holes, though, the Planck mass, being equal to that of an average grain of dust, is quite tiny. And so, physicists who speculated that tiny black holes and elementary particles might be closely related immediately ran up against the incompatibility between general relativity, the theoretical heart of black holes, and quantum mechanics. In the past, the incompatibility stymied all progress in this intriguing direction. Does string theory allow us to go forward? Point 1. Notice that this is different from Figure 11.6, in which a one-dimensional string, as it moves through time, lassos a two-dimensional sphere. Figure 13.1 should be viewed as a snapshot taken at one instant in time. Similarly, in Figure 13.1, we see that a two-dimensional membrane, a two-brane, can wrap around and completely cover a two-dimensional sphere, much as a piece of plastic wrap can be tightly wrapped around the surface of an orange. Although it's harder to visualize, Strominger followed the pattern and realized that the newly discovered three-dimensional ingredients in string theory, the three branes, can wrap around and completely cover a three-dimensional sphere. Having seen clear to this insight, Strominger then showed with a simple and standard physics calculation that the wrapped three-brane provides a tailor-made shield that exactly cancels all of the potentially cataclysmic effects that string theorists had previously feared would occur if a three-dimensional sphere were to collapse. This was a wonderful and important insight. But its full power was not revealed until a short time later, tearing the fabric of space, with conviction. One of the most exciting things about physics is how the state of knowledge can change literally overnight. The morning after Strominger posted his paper on the Electronic Internet Archive, I read it in my office at Cornell after having retrieved it from the World Wide Web. In one stroke, Strominger had made use of the exciting new insights of string theory to resolve one of the thorniest issues surrounding the curling up of extra dimensions into a Calabi-Yau space. But, as I pondered his paper, it struck me that he might have worked out only half of the story. In the earlier space-tearing flop transition work described in the Chapter 11, we had studied a two-part process in which a two-dimensional sphere pinches down to a point, causing the fabric of space to tear, and then the two-dimensional sphere reinflates in a new way, thereby repairing the tear. In Strominger's paper, he had studied what happens when a three-dimensional sphere pinches down to a point, and had shown that the newfound extended objects in string theory ensure that physics continues to be perfectly well behaved. But that's where his paper stopped. Might it be that there was another half to the story, involving once again the tearing of space and its subsequent repair through the reinflation of spheres? Dave Morrison was visiting me at Cornell during the spring term of 1995, and that afternoon we got together to discuss Strominger's paper. Within a couple of hours, we had an outline of what the second half of the story might look like. Drawing on some insights from the late 1980s of the mathematicians Herb Clemens of the University of Utah, Robert Friedman of Columbia University, and Miles Reed of the University of Warwick, as applied by Candelas, Greene, and Tristan Hubsch, then of the University of Texas at Austin, we realized that when a three-dimensional sphere collapses, it may be possible for the Calabi-Yau space to tear and subsequently repair itself by reinflating the sphere. But there is an important surprise. Whereas the sphere that collapsed had three dimensions, the one that reinflates has only two. It's hard to picture what this looks like, but we can get an idea by focusing on a lower-dimensional analogy. Rather than the hard-to-picture case of a three-dimensional sphere collapsing and being replaced by a two-dimensional sphere, let's imagine a one-dimensional sphere collapsing and being replaced by a zero-dimensional sphere. First of all, what are one- and zero-dimensional spheres? Well, let's reason by analogy. A two-dimensional sphere is the collection of points in three-dimensional space that are the same distance from a chosen center, as shown in Figure 13.2. A. By following the same idea, a one-dimensional sphere is the collection of points in two-dimensional space, the surface of this page, for example, that are the same distance from a chosen center, as shown in Figure 13.2b. This is nothing but a circle. Finally, following the pattern, a zero-dimensional sphere is the collection of points in a one-dimensional space, a line, that are the same distance from a chosen center. As shown in Figure 13.2c, this amounts to 2 points, with the radius of the zero-dimensional sphere equal to the distance each point is from their common center, And so, the lower dimensional analogy alluded to in the preceding paragraph involves a circle, a one-dimensional sphere, pinching down, followed by space tearing, and then being replaced by a zero-dimensional sphere. 2 points. Figure 13.3 puts this abstract idea into practice. We imagine beginning with the surface of a donut, in which a one-dimensional sphere, a circle, is embedded as highlighted in figure 13.3. Now, let's imagine that as time goes by, the highlighted circle collapses, causing the fabric of space to pinch. We can repair the pinch by allowing the fabric to momentarily tear and then replacing the pinched one-dimensional sphere, the collapsed circle, with a zero-dimensional sphere 2, points plugging the holes in the upper and lower portions of the shape arising from the tear. As shown in Figure 13.3, the resulting shape looks like a warped banana, which through gentle deformation, non-space tearing, can be reshaped smoothly into the surface of a beach ball. We see, therefore, that when a one-dimensional sphere collapses and is replaced by a zero-dimensional sphere, the topology of the original donut, that is, its fundamental shape, is drastically altered. In the context of the curled-up spatial dimensions, the space-tearing progression of Figure 13.3 would result in the universe depicted in Figure 8.8 evolving into that depicted in Figure 8.7. Although this is a lower-dimensional analogy, it captures the essential features of what Morrison and I foresaw for the second half of Strominger's story. After the collapse of a three-dimensional sphere inside a Calabi-Yau space, it seemed to us that space could tear and subsequently repair itself by growing a two-dimensional sphere, leading to far more drastic changes in topology than Witten and we had found in our earlier work, discussed in Chapter 11. In this way, one Calabi-Yau shape could, in essence, transform itself into a completely different Calabi-Yau shape, much like the donut transforming into the beach ball in Figure 13.3, while string physics remained perfectly well-behaved. Although a picture was starting to emerge, we knew that there were significant aspects that we would need to work out before we could establish that our second half of the story did not introduce any singularities, that is, pernicious and physically unacceptable consequences. We each went home that evening with the tentative elation that we were sitting on a major new insight, a flurry of email. The next morning I received an email from Strominger asking me for any comments or reactions to his paper. He mentioned that it should tie in somehow with your work with Aspinwall and Morrison, because, as it turned out, he too had been exploring a possible connection to the phenomenon of topology change. I immediately sent him an email describing the rough outline Morrison and I had come up with. When he responded, it was clear that his level of excitement matched what Morrison and I had been writing since the preceding day. During the next few days, a continuous stream of email messages circulated between the three of us, as we sought feverishly to put quantitative rigor behind our idea of drastic space-tearing topology change. Slowly but surely, all the details fell into place. By the following Wednesday, a week after Strominger posted his initial insight, we had a draft of a joint paper spelling out the dramatic new transformation of the spatial fabric that can follow the collapse of a three-dimensional sphere. Strominger was scheduled to give a seminar at Harvard the next day, and so left Santa Barbara in the early morning. We agreed that Morrison and I would continue to fine-tune the paper and then submit it to the electronic archive that evening. By 11:45 p.m., we had checked and rechecked our calculations, and everything seemed to hang together perfectly. And so, we electronically submitted our paper and headed out of the physics building. As Morrison and I walked toward my car, I was going to drive him to the house he had rented for the term. Our discussion turned to one of devil's advocacy, in which we imagined the harshest criticisms that someone determined not to accept our results might level. As we drove out of the parking lot and left the campus, we realized that although our arguments were strong and convincing, they were not thoroughly airtight. Neither of us felt that there was any real chance that our work was wrong, but we did recognize that the strength of our claims and the particular wording we had chosen at a few points in the paper might leave the ideas open to rancorous debate, potentially obscuring the importance of the results. We agreed that it might have been better had we written the paper in a somewhat lower key, underplaying the depth of the claims, and allowing the physics community to judge the paper on its merits, rather than possibly reacting to the form of its presentation. As we drove on, Morrison reminded me that under the rules of the Electronic Archive, we could revise our paper until 2 a.m., when it would then be released for public internet access. I immediately turned the car around, and we drove back to the physics building, retrieved our initial submission, and set to work on toning down the prose. Thankfully, it was quite easy to do. A few word changes in critical paragraphs softened the edge of our claims without compromising the technical content. Within an hour, we resubmitted the paper and agreed not to talk about it at all during the drive to Morrison's house. By early the next afternoon, it was evident that the response to our paper was enthusiastic. Among the many email responses was one from Plesser, who gave us one of the highest compliments one physicist can give another by declaring, "I wish that I had thought of that." Notwithstanding our fears the previous night, we had convinced the string theory community that not only can the fabric of space undergo the mild tears discovered earlier, Chapter 11, but that far more drastic rips, roughly illustrated by Figure 1.3.3 Compama, can occur as well, returning to black holes and elementary particles. We have seen the surprising answer to this question was that not much happens at all. For conifold transitions, the technical name for the drastic space-tearing transitions we had now found, there is once again no physical catastrophe, as there would be in conventional general relativity, but there are more pronounced observable consequences. Two related notions underlie these observable consequences. We will explain each in turn. First, as we have discussed, Strominger's initial breakthrough was his realization that a three-dimensional sphere inside a Calabi-Yau space can collapse without an ensuing disaster, because a three-brane wrapped around it provides a perfect protective shield. But what does such a wrapped brane configuration look like? The answer comes from earlier work of Horowitz and Strominger, which showed that to persons such as ourselves who are directly cognizant only of the three extended spatial dimensions, the three-brane smeared around the three-dimensional sphere will set up a gravitational field that looks like that of a black hole. This is not obvious and becomes clear only from a detailed study of the equations governing the branes. Again, it's hard to draw such a higher dimensional configurations accurately on a page, but Figure 13.4 conveys the rough idea with a lower dimensional analogy involving two-dimensional spheres. We see that a two-dimensional membrane can smear itself around a two-dimensional sphere, which itself is sitting inside a Calabi-Yau space positioned at some location in the extended dimensions. Someone looking through the extended dimensions toward this location will sense the wrapped brane by its mass and the force charges it carries, properties that Horowitz and Strominger had shown would look just like those of a black hole. Moreover, in Strominger's 1995 breakthrough paper, he argued that the mass of the three-brane, the mass of the black hole, that is proportional to the volume of the three-dimensional sphere it wraps. The bigger the volume of the sphere, the bigger the three-brane must be in order to wrap around it, and the more massive it becomes. Similarly, the smaller the volume of the sphere, the smaller the mass of the three-brane that wraps it. As this sphere collapses then, a three-brane that wraps around the sphere, which is perceived as a black hole, appears to become ever lighter. When the three-dimensional sphere has collapsed to a pinched point, the corresponding black hole, brace yourself, is massless. Although it sounds completely mysterious, what in the world is a massless black hole? We will soon connect this enigma with more familiar string physics. The second ingredient we need to recall is that the number of holes in a Calabi-Yau shape, as discussed in Chapter 9, determines the number of low-energy, and hence low-mass, vibrational string patterns, the patterns that can possibly account for the particles in Table 1.1, as well as the force carriers. Since the space-tearing conifold transitions change the number of holes, as for example in Figure 1.3.3, in which the hole of the donut is eliminated by the tearing repairing process, how black is black? As it turns out, Hawking too had thought of the analogy between his black hole area increase law and the law of inevitable increase of entropy, but he dismissed it as nothing more than a coincidence. After all, Hawking argued, based upon his area increase law and other results he had found with James Bardeen and Brandon Carter, if one did take the analogy between the laws of black holes and the laws of thermodynamics seriously, not only would one be forced to identify the area of the black hole's event horizon with entropy, but it turns out that one would also have to assign a temperature to the black hole, with the precise value determined by the strength of the black hole's gravitational field at its event horizon. But if a black hole has a non-zero temperature, no matter how small, the most basic and well-established physical principles would require it to emit radiation, much like a glowing poker. But black holes, as everyone knows, are black. They supposedly do not emit anything. Hawking and most everyone else agreed that this definitively ruled out Bekenstein's suggestion. Instead, Hawking was willing to accept that if matter-carrying entropy is dropped into a black hole, this entropy is lost. Plain and simple. So much for the second law of thermodynamics. This was the case until Hawking in 1974 discovered something truly amazing. Black holes, Hawking announced, are not completely black. If one ignores quantum mechanics and invokes only the laws of classical general relativity, then, as originally found some 6 decades previously, black holes certainly do not allow anything, not even light, to escape their gravitational grip. But the inclusion of quantum mechanics modifies this conclusion in a profound way. Even though he was not in possession of a quantum mechanical version of general relativity, Hawking was able to finesse a partial union of these two theoretical tools that yielded some limited, yet reliable results. And the most important result he found was that black holes do emit radiation, quantum mechanically. The calculations are long and arduous, but Hawking's basic idea is simple. We have seen that the uncertainty principle ensures that even the vacuum of empty space is a teeming, roiling frenzy of virtual particles momentarily erupting into existence and subsequently annihilating one another. This jittery quantum behavior also occurs in the region of space just outside the event horizon of a black hole. Hawking realized, however, that the gravitational might of the black hole can inject energy into a pair of virtual photons, say, that tears them just far enough apart so that one gets sucked into the hole. With its partner having disappeared into the abyss of the hole, the other photon of the pair no longer has a partner with which to annihilate. Instead, Hawking showed that the remaining photon gets an energy boost from the gravitational force of the black hole, and, as its partner falls inward, it gets shot outward, away from the black hole. Hawking realized that to someone looking at the black hole from the safety of afar, the combined effect of this tearing apart of virtual photon pairs, happening over and over again all around the horizon of the black hole, will appear as a steady stream of outgoing radiation. Black holes glow. Moreover, Hawking was able to calculate the temperature that a far-off observer would associate with the emitted radiation, and found that it is given by the strength of the gravitational field at the black hole's horizon, exactly as the analogy between the laws of black hole physics and the laws of thermodynamics suggested. Bekenstein was right. Hawking's results showed that the analogy should be taken seriously. In fact, these results showed that it is much more than an analogy. It is an identity. A black hole has entropy. A black hole has temperature. And the gravitational laws of black hole physics are nothing but a rewriting of the laws of thermodynamics in an extremely exotic gravitational context. This was Hawking's 1974 bombshell. To give you a sense of the scales involved, it turns out that when one carefully accounts for all of the details, a black hole whose mass is about 3 times that of the Sun has a temperature of about 100 millionth of a degree above absolute zero. It's not zero, but only just. Black holes are not black, but only barely. Unfortunately, this makes a black hole's emitted radiation meager and impossible to detect experimentally. There is, however, an exception. Hawking's calculations also showed that the less massive a black hole is, the higher its temperature and the greater the radiation it emits. For instance, a black hole as light as a small asteroid would emit about as much radiation as a 1,000,000 megaton hydrogen bomb, with radiation concentrated in the gamma-ray part of the electromagnetic spectrum, Astronomers have searched the night sky for such radiation, but except for a few long-shot possibilities, they have come up empty-handed, a likely indication that such low-mass black holes, if they exist, are very rare. As Hawking often jokingly points out, this is too bad, for if the black hole radiation that his work predicts were to be detected, he would undoubtedly win a Nobel Prize. By contrast, with its tiny, sub-millionth of a degree temperature, when one calculates the entropy of, say, a 3 solar mass black hole, the result is an absolutely enormous number, a 1 followed by about 78 zeros, and the more massive the hole, the greater the entropy. The success of Hawking's calculations unequivocally established that this truly reflects the enormous amount of disorder embodied by a black hole. But disorder of what? As we have seen, black holes appear to be terribly simple objects. So what is the source of this overwhelming disorder? On this question, Hawking's calculations were completely silent. His partial merger of general relativity and quantum mechanics could be used to find the numerical value of a black hole's entropy, but offered no insight into its microscopic meaning. For nearly a quarter of a century, some of the greatest physicists tried to understand what possible microscopic properties of black holes could account for their entropy. But without a fully trustworthy amalgam of quantum mechanics and general relativity, glimpses of an answer may have been uncovered, but the mystery remained unsolved. Enter string theory. Or it did until January 1996, when Strominger and Vafa, building on earlier insights of Susskind and Sen, released a paper to the Electronic Physics Archive entitled Microscopic Origin of the Bekenstein-Hawking Entropy. In this work, Strominger and Vafa were able to use string theory to identify the microscopic constituents of a certain class of black holes and to calculate precisely their associated entropy. Their work relied on the newfound ability to partially circumvent the perturbative approximations in use during the 1980s and early 1990s, and the result they found agreed exactly with that predicted by Bekenstein and Hawking, finally completing a picture partially painted more than 2 decades previously. Strominger and Vafa focused on the class of so-called extremal black holes. These are black holes that are imbued with charge. You can think of it as electric charge, and that, moreover, have the minimal possible mass consistent with the charge they carry. As can be seen from this definition, they are closely related to the BPS states discussed in Chapter 12. In fact, Strominger and Vafa exploited this similarity to the hilt. They showed that they could build, theoretically of course, certain extremal black holes by starting with a particular collection of BPS brains of certain specified dimensions, and binding them together according to a precise mathematical blueprint, in much the same way that an atom can be built, theoretically again, by starting with a bunch of quarks and electrons, and then precisely arranging them into protons and neutrons surrounded by orbiting electrons. Strominger and Vafa showed how some of the newfound ingredients in string theory could similarly be molded together to yield particular black holes. In actuality, black holes are one possible end product of stellar evolution. After a star has burned all its nuclear fuel through billions of years of atomic fusion, it no longer has the strength, the outward-directed pressure to withstand the enormous inward force of gravity. Under a broad spectrum of conditions, this results in a cataclysmic implosion of the star's enormous mass. It violently collapses under its own tremendous weight, forming a black hole. Contrary to this realistic means of formation, Strominger and Vafa advocated designer black holes. They turned the tables on black hole formation by showing how they could be systematically constructed, in a theorist's imagination, by carefully, slowly, and meticulously weaving together a precise combination of the brains that had emerged from the second superstring revolution. The power of this approach became immediately clear. By maintaining full theoretical control over the microscopic construction of their black holes, Strominger and Vafa could easily and directly count the number of rearrangements of the black hole's microscopic constituents that would leave its overall observable properties, its mass and force charges, unchanged. They could then compare this number with the area of the black hole's horizon, the entropy predicted by Bekenstein and Hawking. When Strominger and Vafa did so, they found perfect agreement. At least for the class of extremal black holes, they had succeeded in using string theory to account for the microscopic constituents and the associated entropy precisely. A quarter-century-old puzzle had been solved. Many string theorists view this success as an important and convincing piece of evidence in support of the theory. Our understanding of string theory is still too coarse to be able to make direct and precise contact with 8 experimental observations of, say, the mass of a quark or an electron. But we now see that string theory has provided the first fundamental explanation of a long-established property of black holes that has stumped physicists using more conventional theories for many years. And this property of black holes is intimately tied up with Hawking's prediction that they should radiate, a prediction that in principle should be experimentally measurable. Of course, this requires that we definitively find a black hole in the heavens and then construct equipment sensitive enough to detect the radiation that it emits. If the black hole were light enough, the latter step is well within the reach of current technology, even though this experimental program has not as yet met with success. It does re-emphasize that the chasm between string theory and definitive physical statements about the natural world can be bridged. Even Sheldon Glashow, the arch-rival of string theory through the 1980s, has said recently, "When string theorists talk about black holes, they're almost talking about observable phenomena, and that is impressive. The remaining mysteries of black holes, even with these impressive developments. There are still 2 central mysteries surrounding black holes. The first surrounds the impact black holes have on the concept of determinism. In the beginning of the 19th century, the French mathematician Pierre-Simon de Laplace enunciated the strictest and most far-reaching consequence of the clockwork universe that followed from Newton's laws of motion, an intelligence that, at a given instant, could comprehend all the forces by which nature is animated and the respective situation of the beings that make it up. If moreover it were vast enough to submit these data to analysis, would encompass in the same formula the movements of the greatest bodies of the universe and those of the lightest atoms. For such an intelligence nothing would be uncertain, and the future, like the past, would be open to its eyes. In other words, if at some instant you know the positions and velocities of every particle in the universe, you can use Newton's laws of motion to determine, at least in principle, their positions and velocities at any other prior or future time. From this perspective, any and all occurrences, from the formation of the sun to the crucifixion of Christ to the motion of your eyes across this world, strictly follow from the precise positions and velocities of the particulate ingredients of the universe a moment after the Big Bang. This rigid, lockstep view of the unfolding of the universe raises all sorts of perplexing philosophical dilemmas surrounding the question of free will, but its import was substantially diminished by the discovery of quantum mechanics. We have seen that Heisenberg's uncertainty principle undercuts Laplacian determinism because we fundamentally cannot know the precise positions and velocities of the constituents of the universe. Instead, these classical properties are replaced by quantum wave functions, which tell us only the probability that any given particle is here or there, or that it has this or that velocity. The downfall of Laplace's vision, however, does not leave the concept of determinism in total ruins. Wave functions, the probability waves of quantum mechanics, evolve in time according to precise mathematical rules such as the Schrödinger equation, or its more precise relativistic counterparts such as the Dirac equation and the Klein-Gordon equation. This informs us that quantum determinism replaces Laplace's classical determinism. Knowledge of the wave functions of all of the fundamental ingredients of the universe at some moment in time allows a vast enough intelligence to determine the wave functions at any prior or future time. Quantum determinism tells us that the probability that any particular event will occur at some chosen time in the future is fully determined by knowledge of the wave functions at any prior time. The probabilistic aspect of quantum mechanics significantly softens Laplacian determinism by shifting inevitability from outcomes to outcome likelihoods, but the latter are fully determined within the conventional framework of quantum theory. In 1976, Hawking declared that even this softer form of determinism is violated by the presence of black holes. Once again, the calculations behind this declaration are formidable, but the essential idea is fairly straightforward. when anything falls into a black hole, its wave function gets sucked in as well. But this means that in the quest to work out wave functions at all future times, our vast enough intelligence will be irreparably shortchanged. To predict the future fully, we need to know all wave functions fully today. But if some have escaped down the abyss of black holes, the information they contain, their way. Answering this question is a central goal of current research. As Hawking has put it, most physicists want to believe that information is not lost, as this would make the world safe and predictable. But I believe that if one takes Einstein's general relativity seriously, one must allow for the possibility that space-time ties itself in knots and that information gets lost in the folds. Determining whether or not information actually does get lost is one of the major questions in theoretical physics today. The second unresolved black hole mystery concerns the nature of space-time at the central point of the whole. A straightforward application of general relativity, going all the way back to Schwarzschild in 1916, shows that the enormous mass and energy crushed together at the black hole's center causes the fabric of space-time to suffer a devastating rift, to be radically warped into a state of infinite curvature, to be punctured by a space-time singularity. One conclusion that physicists drew from this is that since all of the matter that has crossed the event horizon is inexorably drawn to the center of the black hole, and since once there the matter has no future, time itself comes to an end at the heart of a black hole. Other physicists, who over the years have explored the properties of the black hole's core using Einstein's equations, revealed the wild possibility that it might be a gateway to another universe that tenuously attaches to ours only at a black hole's center. Roughly speaking, where time in our universe comes to an end, time in the attached universe just begins. We will take up some of the implications of this mind-boggling possibility in the next chapter. But for now, we want to stress one important point. We must recall the central lesson. Extremes of huge mass and small size leading to unimaginably large density invalidate the sole use of Einstein's classical theory and require that quantum mechanics be brought to bear as well. This leads us to ask, what does string theory have to say about the space-time singularity at the center of a black hole? This is a topic of intense current research, but as with the question of information loss, it has not yet been settled. String theory deftly deals with a variety of other singularities, the rips and tears in space, discussed in Chapter 11 and in the first part of this chapter. But if you have seen one singularity, you have not seen them all. The fabric of our universe can be ripped, punctured, and torn in many different ways. String theory has given us profound insights into some of these singularities, but others, the black hole singularity among them, have so far eluded the string theorists' reach. The essential reason for this, once again, is the reliance on perturbative tools in string theory whose approximations, in this case, cloud our ability to analyze reliably and fully what happens at the deep interior point of a black hole. However, given the recent tremendous progress in non-perturbative methods and their successful application to other aspects of black holes, string theorists have high hopes that it won't be long before the mysteries residing at the center of black holes start to unravel. Chapter 14. Reflections on Cosmology. Humans throughout history have had a passionate drive to understand the origin of the universe. There is, perhaps, no single question that so transcends cultural and temporal divides, inspiring the imagination of our ancient forebears as well as the research of the modern cosmologist. At a deep level, there is a collective longing for an explanation of why there is a universe, how it has come to take the form we witness, and for the rationale, the principle, that drives its evolution. The astounding thing is that humanity has now come to a point where a framework is emerging for answering some of these questions scientifically. The currently accepted scientific theory of creation declares that the universe experienced the most extreme of conditions, enormous energy, temperature, and density, during its earliest moments. These conditions, as is by now familiar, require that both quantum mechanics and gravity be taken into account, and hence the birth of the universe provides a profound arena for exercising the insights of superstring theory. We will discuss these nascent insights shortly, But first, we briefly recount the pre-string theory cosmological story, which is often referred to as the Standard Model of Cosmology. The Standard Model of Cosmology. The modern theory of cosmic origins dates from the decade and a half after Einstein's completion of general relativity. Although Einstein refused to take his own theory at face value and accept that it implies that the universe is neither eternal nor static, Alexander Friedmann did. And as we discussed in Chapter 3, Friedmann found what is now known as the Big Bang solution to Einstein's equations, a solution that declares that the universe violently emerged from a state of infinite compression and is currently in the expanding aftermath of that primeval explosion. So certain was Einstein that such time-varying solutions were not a result of his theory that he published a short article claiming to have found a fatal flaw in Friedmann's work. Some 8 months later, however, Friedmann succeeded in convincing Einstein that there was, in fact, no flaw. Einstein publicly but curtly retracted his objection. Nevertheless, it is clear that Einstein did not think Friedmann's results had any relevance to the universe. But about 5 years later, Hubble's detailed observations of a few dozen galaxies with the 100-inch telescope at Mount Wilson Observatory confirmed that, indeed, the universe is expanding. Friedmann's work, refashioned in a more systematic and efficient form by the physicists Howard Robertson and Arthur Walker, still forms the foundation of modern cosmology. In a little more detail, the modern theory of cosmic origins goes like this. Some 15 billion or so years ago, the universe erupted from an enormously energetic, singular event, which spewed forth all of space and all of matter. You don't have to search far to locate where the Big Bang occurred, for it took place where you are now as well as everywhere else. In the beginning, all locations we now see as separate were the same location. The temperature of the universe a mere 10 to the power of minus 43 seconds after the bang, the so-called Planck time, is calculated to have been about 10 to the power of 32 Kelvin, some 10 trillion times hotter than the deep interior of the Sun. As time passed, the universe expanded and cooled, and as it did, the initial homogeneous, roiling hot primordial cosmic plasma began to form eddies and clumps. At about 100,000th of a second after the bang, things had cooled sufficiently, to about 10 trillion Kelvin, about 1,000,000 times hotter than the Sun's interior, for quarks to clump together in groups of 3, forming protons and neutrons. About 100th of a second later, conditions were right for the nuclei of some of the lightest elements in the periodic table to start congealing out of the cooling plasma of particles. For the next 3 minutes, as the simmering universe cooled to about 1 billion degrees, the predominant nuclei that emerged were those of hydrogen and helium, along with trace amounts of deuterium, heavy hydrogen, and lithium. This is known as the period of primordial nucleosynthesis. Not a whole lot happened for the next few 100,000 years, other than further expansion and cooling. But then, when the temperature had dropped to a few thousand degrees, wildly streaming electrons slowed down to the point where atomic nuclei, mostly hydrogen and helium, could capture them, forming the first electrically neutral atoms. This was a pivotal moment. From this point forward, the universe by and large became transparent. Prior to the era of electron capture, the universe was filled with a dense plasma of electrically charged particles, some with positive charges like nuclei and others with negative charges like electrons. Photons, which interact only with electrically charged objects, were bumped and jostled incessantly by the thick bath of charged particles, traversing hardly any distance before being deflected or absorbed. The charged particle barrier to the free motion of photons would have made the universe appear almost completely opaque, much like what you may have experienced in a dense morning fog or a blinding, gusty snowstorm. But when negatively charged electrons were brought into orbit around positively charged nuclei yielding electrically neutral atoms, the charged obstructions disappeared and the dense fog lifted. From that time onward, photons from the Big Bang have traveled unhindered, and the full expanse of the universe gradually came into view. About 1 billion years later, with the universe having substantially calmed down from its frenetic beginnings, galaxies, stars, and ultimately planets began to emerge as gravitationally bound clumps of the primordial elements. Today, some 15 billion or so years after the Bang, we can marvel at both the magnificence of the cosmos and at our collective ability to have pieced together a reasonable and experimentally testable theory of cosmic origin. But how much faith should we really have in the Big Bang Theory? Putting the Big Bang to the test. By looking out into the universe with their most powerful telescopes, astronomers can see light that was emitted from galaxies and quasars just a few billion years after the Big Bang. This allows them to verify the expansion of the universe predicted by the Big Bang Theory back to this early phase of the universe. And everything checks out to a T. To test the theory to yet earlier times, physicists and astronomers must make use of more indirect methods. One of the most refined approaches involves something known as cosmic background radiation. If you've ever felt a bicycle tire after vigorously pumping it full of air, you know that it is warm to the touch. This is because, when things are compressed, they heat up. This is the principle, for example, behind pressure cookers, in which air is tightly compressed within a sealed pot in order for unusually high cooking temperatures to be readily achieved. The reverse is also true. When pressure is released and things are allowed to expand, they cool. If you remove the lid on a pressure cooker, or more spectacularly should it blow off, the air it contains will expand to its ordinary density while cooling to standard room temperature. This is the science underlying the phrase blow-off steam, a familiar approach to cool down a heated situation. It turns out that these simple terrestrial observations have a profound incarnation within the cosmos. We saw above that after electrons and nuclei join together to form atoms, photons are free to travel unimpeded through the universe, much like atoms of air in a hot but otherwise empty pressure cooker. And just as air in the pressure cooker cools down when the lid is removed and it is allowed to expand, the same is true for the gas of photons streaming through the universe as it expands. In fact, physicists as far back as George Gamow and his students Ralph Alpher and Robert Herman in the 1950s, and Robert Dicke and Jim Peebles in the mid-1960s, realized that the present-day universe should be permeated by an almost uniform bath of these primordial photons, which, through the last 15 billion years of cosmic expansion, have cooled to a mere handful of degrees above absolute zero. In 1965, Arno Penzias and Robert Wilson of Bell Laboratories in New Jersey accidentally made one of the most important discoveries of our age when they detected this afterglow of the Big Bang while working on an antenna intended for use with communication satellites. Subsequent research has refined both theory and experiment, culminating in measurements taken by NASA's COBE, Cosmic Background Explorer satellite, in the early 1990s. With these data, physicists and astronomers have confirmed to high precision that the universe is filled with microwave radiation. If our eyes were sensitive to microwaves, we would see a diffuse glow in the world around us, whose temperature is about 2.7 degrees above absolute zero, exactly in keeping with the expectation of the Big Bang Theory. In concrete terms, in every cubic meter of the universe, including the one you now occupy, there are, on average, about 400 million photons that collectively compose the vast cosmic sea of microwave radiation, an echo of creation. A percentage of the snow you see on your television screen when you disconnect the cable feed and tune to a station that has ceased its scheduled broadcasts is, in fact, due to this dim aftermath of the Big Bang. This match between theory and experiment confirms the Big Bang picture of cosmology as far back as the time that photons first moved freely through the universe about a few 100,000 years after the Bang, ATB. Can we push further in our tests of the Big Bang Theory to even earlier times? We can. By using standard principles of nuclear theory and thermodynamics, physicists can make definite predictions about the relative abundance of the light elements produced during the period of primordial nucleosynthesis, between a hundredth of a second and a few minutes ATB. According to theory, for example, about 23% of the universe should be composed of helium. By measuring the helium abundance in stars and nebulae, astronomers have amassed impressive support that, indeed, this prediction is right on the mark. Perhaps even more impressive is the prediction and confirmation regarding deuterium abundance. since there is essentially no astrophysical process other than the Big Bang that can account for its small but definite presence throughout the cosmos. The confirmation of these abundances, and more recently that of lithium, is a sensitive test of our understanding of early universe physics back to the time of their primordial synthesis. This is impressive almost to the point of hubris. All the data we possess confirm a theory of cosmology capable of describing the universe from about 1/100th of a second ATB to the present, some 15 billion years later. Nevertheless, one should not lose sight of the fact that the newborn universe evolved with phenomenal haste. Tiny fractions of a second, fractions much smaller than 1/100th of a second, form cosmic epochs during which long-lasting features of the world were first imprinted. And so, physicists have continued to push onward, trying to explain the universe at ever earlier times. Since the universe gets ever smaller, hotter, and denser as we push back, an accurate quantum mechanical description of matter and the forces becomes increasingly important. As we have seen from other viewpoints in earlier chapters, point-particle quantum field theory works until typical particle energies are around the Planck energy. In a cosmological context, this occurred when the whole of the known universe fit within a Planck-sized nugget, yielding a density so great that it strains one's ability to find a fitting metaphor or an enlightening analogy. The density of the universe at the Planck time was simply colossal. At such energies and densities, gravity and quantum mechanics can no longer be treated as two separate entities as they are in point-particle quantum field theory. Instead, the central message of this book is that at and beyond these enormous energies, we must invoke string theory. In temporal terms, we encounter these energies and densities when we probe earlier than the Planck time of 10, 41 seconds ATB, and hence this earliest epoch is the cosmological arena of string theory. Different. It has a crystalline block structure, which means that if you examine it with adequate precision, it will, like any crystal, look different from different angles. The phase transition has resulted in a decrease in the amount of rotational symmetry that is manifest. Although we have discussed only one familiar example, the point is true more generally. As we lower the temperature of many physical systems, at some point they undergo a phase transition that typically results in a decrease or a breaking of some of their previous symmetries. In fact, a system can go through a series of phase transitions if its temperature is varied over a wide enough range. Water, again, provides a simple example. If we start with H2O above 100 degrees Celsius, it is a gas, steam. In this form, the system has even more symmetry than in the liquid phase since now the individual H2O molecules have been liberated from their congested, stuck-together liquid form. Instead, they all zip around the container on completely equal footing, without forming any clumps or cliques in which groups of molecules single each other out for a close association at the expense of others. Molecular democracy prevails at high enough temperatures. As we lower the temperature below 100 degrees, of course, water droplets do form as we pass through a gas-liquid phase transition, and the symmetry is reduced. Continuing on to yet lower temperatures, nothing too dramatic happens until we pass through 0 degrees Celsius, when, as above, the liquid water/solid ice phase transition results in another abrupt decrease in symmetry. Physicists believe that between the Planck time and 1/100th of a second ATB, the universe behaved in a very similar way, passing through at least two analogous phase transitions. At temperatures above 10 to the power of 28 Kelvin, the three non-gravitational forces appeared as one, as symmetric as they could possibly be. At the end of this chapter, we will discuss string theory's inclusion of the gravitational force into this high-temperature merger. But, as the temperature dropped below 10 to the power of 28 Kelvin, the universe underwent a phase transition in which the three forces crystallized out from their common union in different ways. Their relative strengths and the details of how they act on matter began to diverge. And so, the symmetry among the forces evident at higher temperatures was broken as the universe cooled. Nevertheless, the work of Glashow, Solem, and Weinberg, see Chapter 5, shows that not all of the high-temperature symmetry was erased. The weak and electromagnetic forces were still deeply interwoven. As the universe further expanded and cooled, nothing much happened, until things simmered down to 10 to the power of 15 Kelvin, about 100 million times the sun's core temperature, when the universe went through another phase transition that affected the electromagnetic and weak forces. At this temperature, they too crystallized out from their previous more symmetric union, and as the universe continued to cool, their differences became magnified. The two-phase transitions are responsible for the three apparently distinct non-gravitational forces at work in the world, even though this review of cosmic history shows that the forces, in fact, are deeply related. A cosmological puzzle. This post-Planck-era cosmology provides an elegant, consistent, and calculationally tractable framework for understanding the universe as far back as the briefest moments after the Bang. But, as with most successful theories, our new insights raise yet more detailed questions. And it turns out that some of these questions, while not invalidating the standard cosmological scenario as presented, do highlight awkward aspects that point toward the need for a deeper theory. Let's focus on one. It is called the horizon problem, and it is one of the most important issues in modern cosmology. Detailed studies of the cosmic background radiation have shown that regardless of which direction in the sky one points the measuring antenna, the temperature of the radiation is the same, to about 1 part in 100,000. If you think about it for a moment, you will realize that this is quite strange. Why should different locations in the universe, separated by enormous distances, have temperatures that are so finely matched? A seemingly natural resolution to this puzzle is to note that, yes, two diametrically opposite places in the heavens are far apart today, but like twins separated at birth, during the earliest moments of the universe they and everything else were very close together. Since they emerged from a common starting point, you might suggest that it's not at all surprising that they share common physical traits such as their temperature. In the standard Big Bang cosmology, this suggestion fails. Here's why. A bowl of hot soup gradually cools to room temperature because it is in contact with the colder surrounding air. If you wait long enough, the temperature of the soup and the air will, through their mutual contact, become the same. But if the soup is in a thermos, of course, it retains its heat for much longer, since there is far less communication with the outside environment. This reflects that the homogenization of temperature between two bodies relies on their having prolonged and unimpaired communication. To test the suggestion that positions in space that are currently separated by vast distances share the same temperature because of their initial contact, we must therefore examine the efficacy of information exchange between them in the early universe. At first, you might think that since the positions were closer together at earlier times, communication was ever easier. But spatial proximity is only one part of the story. The other part is temporal duration. To examine this more fully, let's imagine studying a film of the cosmic expansion, but let's review it in reverse, running the film backward in time from today toward the moment of the Big Bang. Since the speed of light sets a limit to how fast any signal or information of any kind can travel, matter in two regions of space can exchange heat energy and thereby have a chance of coming to a common temperature only if the distance between them at a given moment is less than the distance light can have traveled since the time of the Big Bang. And so, as we roll the film backward in time, we see that there is a competition between how close together our spatial regions become versus how far back we have to turn the clock for them to get there. For instance, if in order for the separation of our two spatial locations to be 186,000 miles, we have to run the film back to less than a second ATB, then, even though they are much closer, there is still no way for them to have any influence on each other since light would require a whole second to travel the distance between them. If, in order for their separation to be much less, say 186 miles, we have to run the film back to less than 1,000th of a second ATB, then, again, the same conclusion follows. They can't influence each other since in less than 1,000th of a second, light can't travel the 186 miles separating them. Carrying on in the same vein, if we have to run the film back to less than a billionth of a second ATB in order for these regions to be within 1 foot of each other, they still cannot influence each other since there's just not enough time since the bang for light to have traveled the 12 inches between them. This shows that just because 2 points in the universe get closer and closer as we head back to the bang, it is not necessarily the case that they can have had the thermal contact, like that between soup and air, necessary to bring them to the same temperature. Physicists have shown that precisely this problem arises in the standard Big Bang model. Detailed calculations show that there is no way for regions of space that are currently widely separated to have had the exchange of heat energy that would explain their having the same temperature. As the word horizon refers to how far we can see, how far light can travel, so to speak, physicists call the unexplained uniformity of temperature throughout the vast expanse of the cosmos the horizon problem. The puzzle does not mean the standard cosmological theory is wrong, but the uniformity of temperature does strongly suggest that we are missing an important part of the cosmological story. In 1979, the physicist Alan Guth, now of the Massachusetts Institute of Technology, wrote the missing chapter, Inflation. The root of the horizon problem is that in order to get two widely separated regions of the universe close together, we have to run the cosmic film way back toward the beginning of time. So far back, in fact, that there is not enough time for any physical influence to have traveled from one region to the other. The difficulty, therefore, is that as we run the cosmological film backward and approach the Big Bang, the universe does not shrink at a fast enough rate. Well, that's the rough idea, but it's worthwhile sharpening the description a bit. The horizon problem stems from the fact that, like a ball tossed upward, the dragging pull of gravity causes the expansion rate of the universe to slow down. This means that, for example, to have the separation between two locations in the cosmos, we must run the film back more than halfway toward its beginning. In turn, we see that to have the separation, we must more than have the time since the Big Bang. Less time since the bang, proportionally speaking, means it is harder for the two regions to communicate, even though they get closer. Guth's resolution of the horizon problem is now simple to state. He found another solution to Einstein's equations in which the very early universe undergoes a brief period of enormously fast expansion, a period during which, in fact, it inflates in size at an unheralded exponential expansion rate. Unlike the case of a ball that slows down after being tossed upward, exponential expansion gets faster as it proceeds. When we run the cosmic film in reverse, rapid accelerating expansion turns into rapid decelerating contraction. This means that to have the separation between two locations in the cosmos during the exponential epoch, we need run the film back less than halfway. Much less, in fact. Running the film back less implies that the two regions will have had more time to communicate thermally, and, like hot soup and air, they will have had ample time to come to the same temperature. Through Guth's discovery and later important refinements made by Andre Linde, now of Stanford University, Paul Steinhardt and Andreas Albrecht, then of the University of Pennsylvania, and many others, the standard cosmological model was revamped into the inflationary cosmological model. In this framework, the standard cosmological model is modified during a tiny window of time, around 10 to the power of minus 36 to 10 to the power of minus 34 seconds ATB, in which the universe expanded by a colossal factor of at least 10 to the power 30, compared with a factor of about 100 during the same time interval in the standard scenario. This means that in a brief flicker of time, about a trillionth of a trillionth of a trillionth of a second ATB, the size of the universe increased by a greater percentage than it has in the 15 billion years since. Before this expansion, matter that is now in far-flung regions of the cosmos was much closer together than in the standard cosmological model, making it possible for a common temperature to be easily established. Then, through Guth's momentary burst of cosmological inflation, followed by the more usual expansion of the standard cosmological model, these regions of space were able to become separated by the vast distances we witness currently. And so, the brief but profound inflationary modification of the standard cosmological model solves the horizon problem, as well as a number of other important problems we have not discussed, and has gained wide acceptance among cosmologists. We summarize the history of the universe from just after the Planck time to the present, according to the current theory, cosmology and superstring theory. There remains a sliver of figure 14.1 comma between the Big Bang and the Planck time that we have not yet discussed, but are denser, as we move backward, wrapped around spatial dimensions. Although it's significantly harder to see, if there are 3 or fewer circular spatial dimensions, 2 wrapped strings will likely collide with one another, the analog of what happens for 2 particles moving in one dimension. But in 4 or more space dimensions, wrapped strings are less and less likely ever to collide, the analog of what happens for point particles in 2 or more dimensions. And so we have the following picture. In the first moment of the universe, the tumult from the high but finite temperature drives all of the circular dimensions to try to expand. As they do, the wrapped strings constrict the expansion, driving the dimensions back to their original Planck size radii. But sooner or later, a random thermal fluctuation will drive 3 dimensions momentarily to grow larger than the others, and our discussion then shows that strings which wrap these dimensions are highly likely to collide. About half of the collisions will involve string-antistring pairs, leading to annihilations that continually lessen the constriction, allowing these 3 dimensions to continue to expand. The more they expand, the less likely it is for other strings to get entangled around them, since it takes more energy for a string to wrap around a larger dimension. And so, the expansion feeds on itself, becoming ever less constricted as the dimensions get ever larger. We can now imagine that these 3 spatial dimensions continue to evolve in the manner described in the previous sections, and expand to a size as large as or larger than the currently observable universe. Cosmology and Calabi-Yau shapes. For simplicity, Brandenburger and Waffe imagined that all of the spatial dimensions are circular. In fact, as noted in Chapter 8, so long as the circular dimensions are large enough that they curve back on themselves only beyond the range of our current observational capacity, a circular shape is consistent with the universe we observe. But for dimensions that stay small, a more realistic scenario is one in which they are curled up into a more intricate Calabi-Yau space. Of course, the key question is, which Calabi-Yau space? How is this particular space determined? No one has been able to answer this question, but by combining the drastic topology-changing results described in the preceding chapter with these cosmological insights, we can suggest a framework for doing so. Through the space-tearing conifold transitions, we now know that any Calabi-Yau shape can evolve into any other. So we can imagine that in the tumultuous hot moments after the bang, the curled-up Calabi-Yau component of space stays small, but goes through a frenetic dance in which its fabric rips apart and reconnects over and over again, rapidly taking us through a long sequence of different Calabi-Yau shapes. As the universe cools and 3 of the spatial dimensions get large, the transitions from one Calabi-Yau to another slow down, with the extra dimensions ultimately settling into a Calabi-Yau shape that, optimistically, gives rise to the physical features we observe in the world around us. The challenge facing physicists is to understand in detail the evolution of the Calabi-Yau component of space so that its present form can be predicted from theoretical principles. With the newfound ability of one Calabi-Yau to change smoothly into another, we see that the issue of selecting one Calabi-Yau shape from the many may in fact be reduced to a problem of cosmology, before the beginning, nudged to merge with the other forces, as in figure 14.2, without any special molding of the Calabi-Yau portion of space. Although it is far too early to tell, this may indicate that cosmological unity is more easily achieved by making use of the larger framework of M-theory. The developments discussed in this and the previous sections represent the first, somewhat tentative steps toward understanding the cosmological implications of string/M theory. During the coming years, as the non-perturbative tools of string/M theory are sharpened, physicists anticipate that some of the most profound insights will emerge from their application to cosmological questions. But without currently having methods that are sufficiently powerful to understand cosmology according to string theory fully, it is worthwhile to think about some general considerations concerning the possible role of cosmology in the search for the ultimate theory. We caution that some of these ideas are of a more speculative nature than much of what we have discussed previously, but they do raise issues that any purported final theory may one day have to address. cosmological speculation, and the ultimate theory. Cosmology has the ability to grab hold of us at a deep, visceral level, because an understanding of how things began feels, at least to some, like the closest we may ever come to understanding why they began. That's not to say that modern science provides a connection between the question of how and the question of why. It doesn't. And it may well be that no such scientific connection is ever found, but the study of cosmology does hold the promise of giving us our most complete understanding of the arena of the why, the birth of the universe. And this at least allows for a scientifically informed view of the frame within which the questions are asked. Sometimes attaining the deepest familiarity with a question is our best substitute for actually having the answer. In the context of searching for the ultimate theory, these lofty reflections on cosmology give way to far more concrete considerations. The way things in the universe appear to us today, way on the far right-hand side of the timeline in Figure 14.1, depends upon the fundamental laws of physics to be sure, but it may also depend on aspects of cosmological evolution from the far left-hand side of the timeline that potentially lie outside the scope of even the deepest theory. It's not hard to imagine how this might be. Think of what happens, for example, when you toss a ball in the air. The laws of gravity govern the ball's subsequent motion, but we can't predict where the ball will land exclusively from those laws. We must also know the velocity of the ball, its speed and direction as it left your hand. That is, we must know the initial conditions of the ball's motion. Similarly, there are features of the universe that also have a historical contingency. The reason why a star formed here or a planet there depends upon a complicated chain of events that, at least in principle, we can imagine tracing back to some feature of how the universe was when it all began. But it is possible that even more basic features of the universe, perhaps even the properties of the fundamental matter and force particles, also have a direct dependence on historical evolution. Evolution that itself is contingent upon the initial conditions of the universe. In fact, we've already noted one possible incarnation of this idea in string theory. As the hot, early universe evolved, the extra dimensions may have transmuted from shape to shape, ultimately settling down to one particular Calabi-Yau space once things had cooled off sufficiently. But, like a ball tossed in the air, the result of that journey through numerous Calabi-Yau shapes may well depend on details of how the journey got started in the first place. And through the influence of the resulting Calabi-Yau shape on particle masses and on properties of forces, we see that cosmological evolution and the state of the universe when it began can have a profound impact on the physics we currently observe. We don't know what the initial conditions of the universe were, or even the ideas, concepts, and language that should be used to describe them. We believe that the outrageous initial state of infinite energy, density, and temperature that arises in the standard and inflationary cosmological models is a signal that these theories have broken down rather than a correct description of the physical conditions that actually existed. String theory offers an improvement by showing how such infinite extremes might be avoided. Nevertheless, no one has any insight on the question of how things actually did begin. In fact, our ignorance persists on an even higher plane. We don't know whether the question of determining the initial conditions is one that is even sensible to ask, or whether, like asking general relativity to give insight into how hard you happen to toss a ball in the air, it is a question that lies forever beyond the grasp of any theory. Valiant attempts by physicists such as Hawking and James Hartle of the University of California at Santa Barbara have tried to bring the question of cosmological initial conditions within the umbrella of physical theory, but all such attempts remain inconclusive. In the context of string/M theory, our cosmological understanding is, at present, just too primitive to determine whether our candidate theory of everything truly lives up to its name and determines its own cosmological initial conditions, thereby elevating them to the status of physical law. This is a prime question for future research. But even beyond the issue of initial conditions and their impact on the ensuing historical twists and turns of cosmic evolution, some recent and highly speculative proposals have argued for yet other potential limits on the explanatory power of any final theory. No one knows if these ideas are right or wrong, and certainly they currently lie on the outskirts of mainstream science, but they do highlight, albeit in a rather provocative and speculative manner, an obstacle that any proposed final theory may encounter. The basic idea rests upon the following possibility. Imagine that what we call the universe is actually only one tiny part of a vastly larger cosmological expanse, one of an enormous number of island universes scattered across a grand cosmological archipelago. Although this might sound rather far-fetched, and in the end it may well be, Andre Linde has suggested a concrete mechanism that might lead to such a gargantuan universe. Linde has found that the brief but crucial burst of inflationary expansion discussed earlier may not have been a unique one-time event. Instead, he argues, the conditions for inflationary expansion may happen repeatedly in isolated regions peppered throughout the cosmos, which then undergo their own inflationary ballooning in size, evolving into new separate universes. And in each of these universes the process continues, with new universes sprouting from far-flung regions in the old, generating a never-ending web of ballooning cosmic expanses. The terminology gets a little cumbersome, but let's follow fashion and call this greatly expanded notion of the universe the multiverse, with each of the constituent parts being called a universe. The central observation is that whereas in Chapter 7 we noted that everything we know points toward a consistent and uniform physics throughout our universe, this may have no bearing on the physical attributes in these other universes so long as they are separate from us, or at least so far away that their light has not had time to reach us. And so we can imagine that physics varies from one universe to another. In some, the differences may be subtle. For example, the electron mass, or the strength of the strong force, might be 0.001% larger or smaller than in our universe. In others, physics may differ in more pronounced ways. The up quark might weigh 10 times what it weighs in our universe, or the strength of the electromagnetic force might be 10 times the value we measure, with all the profound implications that this has on stars and on life as we know it, as indicated in Chapter 1. And in other universes, physics may differ in still more dramatic ways. The list of elementary particles and forces may be completely distinct from ours, or, taking a cue from string theory, even the number of extended dimensions may differ, with some cramped universes having as few as 0 or 1 large spatial dimension, while other expansive universes possess 8, 9, or even 10 extended spatial dimensions. If we let our imaginations run free, even the laws themselves can drastically differ from universe to universe. The range of possibilities is endless. Here's the point. If we scan through this huge maze of universes, the vast majority will not have conditions hospitable to life, or at least to anything remotely akin to life as we know it. For drastic changes in familiar physics, this is clear. If our universe truly looked like the garden hose universe, life as we know it would not exist. But even rather conservative changes to physics would interfere with the formation of stars, for example, disrupting their ability to act as cosmic furnaces that synthesize complex life-supporting atoms such as carbon and oxygen that, normally, are spewed throughout the universe by supernova explosions. In light of the sensitive dependence of life on the details of physics, if we now ask, for instance, why the forces and particles of nature have the particular properties we observe, a possible answer emerges. Across the entire multiverse, these features vary widely. Their properties can be different and are different in other universes. What's special about the particular combination of particle and force properties we observe is that, clearly, they allow life to form. And life, intelligent life in particular, is a prerequisite even to ask the question of why our universe has the properties it does. In plain language, things are the way they are in our universe because if they weren't, we wouldn't be here to notice, like the winners of a mass game of Russian roulette, whose surprise at surviving is tempered by the realization that, had they not won, they wouldn't have been able not to feel surprised. The multiverse hypothesis has the capacity to lessen our insistence on explaining why our universe appears as it does. This line of argument is a version of an idea with a long history known as the anthropic principle. As presented, it is a perspective that is diametrically opposed to the dream of a rigid, fully predictive, unified theory in which things are the way they are, because the universe could not be otherwise. Rather than being the epitome of poetic grace in which everything fits together with inflexible elegance, the multiverse and the anthropic principle paint a picture of a wildly excessive collection of universes with an insatiable appetite for variety. It will be extremely hard, if not impossible, for us ever to know if the multiverse picture is true. Even if there are other universes, we can imagine that we will never come into contact with any of them. But by vastly increasing the scope of what's out there, in a manner that dwarfs Hubble's realization that the Milky Way is but one galaxy among many, the concept of the multiverse does at least alert us to the possibility that we may be asking too much of an ultimate theory. We should require that our ultimate theory give a quantum mechanically consistent description of all forces and all matter. We should require that our ultimate theory give a cogent cosmology within our universe. However, if the multiverse picture is correct, a huge if, it may be asking too much for our theory to explain as well the detailed properties of the particle masses, charges, and the force strengths. But we must emphasize that even if we accept the speculative premise of the multiverse, the conclusion that this compromises our predictive power is far from airtight. The reason, simply put, is that if we unleash our imaginations and allow ourselves to contemplate a multiverse, we should also unleash our theoretical musings and contemplate ways in which the apparent randomness of the multiverse can be tamed. For one relatively conservative musing, we can imagine that, were the multiverse picture true, we would be able to extend our ultimate theory to its full, sprawling expanse, and that our extended ultimate theory might tell us precisely why and how the values of the fundamental parameters are sprinkled across the constituent universes. A more radical musing comes from a proposal of Lee Smolin of Penn State University, who, inspired by the similarity between conditions at the Big Bang and at the centers of black holes, each being characterized by a colossal density of crushed matter, has suggested that every black hole is the seed for a new universe that erupts into existence through a big bang-like explosion, but is forever hidden from our view by the black hole's event horizon. Beyond proposing another mechanism for generating a multiverse, Smolin has injected a new element, a cosmic version of genetic mutation, that does an end run around the scientific limitations associated with the anthropic principle. Imagine, he suggests, that when a universe sprouts from the core of a black hole, its physical attributes, such as particle masses and force strengths, are close, but not identical, to those of its parent universe. Since black holes arise from extinguished stars, and star formation depends upon the precise values of the particle masses and force strengths, the fecundity of any given universe, the number of black hole progeny it can produce, depends sensitively on these parameters. Small variations in the parameters of the progeny universes will therefore lead to some that are even more optimized for black hole production than their parent universe, and have an even greater number of offspring universes of their own. After many generations, the descendants of universes optimized for producing black holes will thus be so numerous that they will overwhelm the population of the multiverse. And so, rather than invoking the anthropic principle, Smolin's suggestion provides a dynamic mechanism that, on average, drives the parameters of each next-generation universe ever closer to particular values, those that are optimum for black hole production. This approach gives another method, even in the context of the multiverse, in which the fundamental matter and force parameters can be explained. If Smolin's theory is right, and if we are a typical member of a mature multiverse, these are big ifs and can be debated on many fronts, of course, the parameters of the particles and forces that we measure should be optimized for black hole production. That is, any fiddling with these parameters of our universe should make it harder for black holes to form. Physicists have begun to investigate this prediction. At present, there is no consensus on its validity. But even if Smolin's specific proposal turns out to be wrong, it does present yet another shape that the ultimate theory might take. The ultimate theory may, at first sight, appear to lack rigidity. We may find that it can describe a wealth of universes, most of which have no relevance to the one we inhabit. And moreover, we can imagine that this wealth of universes may be physically realized, leading to a multiverse, something that, at first sight, forever limits our predictive power. In fact, however, this discussion illustrates that an ultimate explanation can yet be achieved, so long as we grasp not only the ultimate laws, but also their implications for cosmological evolution on an unexpectedly grand scale. Undoubtedly, the cosmological implications of string/M theory will be a major field of study well into the 21st century. Without accelerators capable of producing Planck-scale energies, we will increasingly have to rely on the cosmological accelerator of the Big Bang, and the relics it has left for us throughout the universe for our experimental data. With luck and perseverance, we may finally be able to answer questions such as how the universe began and why it has evolved to the form we behold in the heavens and on Earth. There is, of course, much uncharted territory between where we are and where full answers to these fundamental questions lie, but the development of a quantum theory of gravity through superstring theory lends credence to the hope that we now possess theoretical tools for pushing into the vast regions of the unknown, and, no doubt after many a struggle, possibly emerging with answers to some of the deepest questions ever posed. Part 5, Unification in the 21st Century. Chapter 15, Prospects. Centuries from now, superstring theory, or its evolution within M theory, may have developed so far beyond our current formulation that it might be unrecognizable even to today's leading researchers. As we continue to seek the ultimate theory, we may well find that string theory is but one of many pivotal steps on a path toward a far grander conception of the cosmos, a conception that involves ideas that differ radically from anything we have previously encountered. The history of science teaches us that each time we think that we have it all figured out, nature has a radical surprise in store for us that requires significant and sometimes drastic changes in how we think the world works. Then again, in a bit of brash posturing, we can also imagine, as others before us have perhaps naively done, that we are living through a landmark period in humanity's history in which the search for the ultimate laws of the universe will finally draw to a close. As Edward Witten has said, I feel that we are so close with string theory that, in my moments of greatest optimism, I imagine that any day the final form of the theory might drop out of the sky and land in someone's lap. But, more realistically, I feel that we are now in the process of constructing a much deeper theory than anything we have had before, and that well into the 21st century, when I am too old to have any useful thoughts on the subject, younger physicists will have to decide whether we have in fact found the final theory. Although we are still feeling the aftershocks of the second superstring revolution and absorbing the panoply of new insights that it has engendered, most string theorists agree that it will likely take a third and maybe a fourth such theoretical upheaval before the full power of string theory is unleashed and its possible role as the final theory assessed. As we have seen, string theory has already painted a remarkable new picture of how the universe works, but there are significant hurdles and loose ends that will no doubt be the primary focus of string theorists in the 21st century. And so, in this last chapter we will not be able to finish telling the story of humanity's search for the deepest laws of the universe, because the search continues. Instead, let's guide our gaze into the future of string theory by discussing 5 central questions string theorists will face as they continue the pursuit of the ultimate theory. What is the fundamental principle underlying string theory? One overarching lesson we have learned during the past 100 years is that the known laws of physics are associated with principles of symmetry. Special relativity is based on the symmetry embodied in the principle of relativity, the symmetry between all constant velocity vantage points. The gravitational force, as embodied in the general theory of relativity, is based on the equivalence principle, the extension of the principle of relativity to embrace all possible vantage points regardless of the complexity of their states of motion. And the strong, weak, and electromagnetic forces are based on the more abstract gauge symmetry principles. Physicists, as we have discussed, tend to elevate symmetry principles to a place of prominence by putting them squarely on the pedestal of explanation. Gravity, in this view, exists in order that all possible observational vantage points are on completely equal footing, i.e., so that the equivalence principle holds. Similarly, the non-gravitational forces exist in order that nature respect their associated gauge symmetries. Of course, this approach shifts the question of why a certain force exists to why nature respects its associated symmetry principle, but this certainly feels like progress, especially when the symmetry in question is one that seems eminently natural. For example, why should one observer's frame of reference be treated differently from another's? It seems far more natural for the laws of the universe to treat all observational vantage points equally. This is accomplished through the equivalence principle and the introduction of gravity into the structure of the cosmos. Although it requires some mathematical background to appreciate fully, as we indicated in Chapter 5, there is a similar rationale behind the gauge symmetries underlying the three non-gravitational forces. String theory takes us down another notch on the scale of explanatory depth because all of these symmetry principles, as well as another, supersymmetry, emerge from its structure. In fact, had history followed a different course, and had physicists come upon string theory some 100 years earlier, we can imagine that the symmetry principles would have all been discovered by studying its properties. But bear in mind that whereas the equivalence principle gives us some understanding of why gravity exists, and the gauge symmetries give us some sense of why the non-gravitational forces exist, in the context of string theory, these symmetries are consequences. Although their importance is in no way diminished, they are part of the end product of a much larger theoretical structure. This discussion brings the following question into sharp relief. Is string theory itself an inevitable consequence of some broader principle, possibly but not necessarily a symmetry principle, in much the same way that the equivalence principle inexorably leads to general relativity, or that gauge symmetries lead to the non-gravitational forces? As of this writing, no one has any insight into the answer to this question. To appreciate its importance, we need only imagine Einstein trying to formulate general relativity without having had the happy thought he experienced in the Berne Patent Office in 1907 that led him to the principle of equivalence. It would not have been impossible to formulate general relativity without first having this key insight, but it certainly would have been extremely difficult. The equivalence principle provides a succinct, systematic, and powerful organizational framework for analyzing the gravitational force. The description of general relativity we gave in Chapter 3, for example, relied centrally on the equivalence principle, and its role in the full mathematical formalism of the theory is even more crucial. Currently, string theorists are in a position analogous to an Einstein bereft of the equivalence principle. Since Veneziano's insightful guess in 1968, the theory has been pieced together, discovery by discovery, revolution by revolution. But a central organizing principle that embraces these discoveries and all other features of the theory within one overarching and systematic framework. A framework that makes the existence of each individual ingredient absolutely inevitable is still missing. The discovery of this principle would mark a pivotal moment in the development of string theory, as it would likely expose the theory's inner workings with unforeseen clarity. There is, of course, no guarantee that such a fundamental principle exists, but the evolution of physics during the last 100 years encourages string theorists to have high hopes that it does. As we look to the next stage in the development of string theory, finding its principle of inevitability, that underlying idea from which the whole theory necessarily springs forth, is of the highest priority. What are space and time, really, and can we do without them? In many of the preceding chapters, we have freely made use of the concepts of space and of spacetime. In Chapter 2, we described Einstein's realization that space and time are inextricably interwoven by the unexpected fact that an object's motion through space has an influence on its passage through time. In Chapter 3, we deepened our understanding of spacetime's role in the unfolding of the cosmos through general relativity, which shows that the detailed shape of the spacetime fabric communicates the force of gravity from one place to another. The violent quantum undulations in the microscopic structure of the fabric, as discussed in Chapters 4 and 5, establish the need for a new theory, leading us to string theory. And finally, in a number of the chapters that followed, we have seen that string theory proclaims that the universe has many more dimensions than we are aware of, some of which are curled up into tiny but complicated shapes that can undergo wondrous transformations in which their fabric punctures, tears, and then repairs itself. Through graphic representations, We have tried to illustrate these ideas by envisioning the fabric of space and spacetime as if it were somewhat like a piece of material out of which the universe is tailored. These images have considerable explanatory power. They are used regularly by physicists as a visual guide in their own technical work. Although staring at figures such as the ones just mentioned gives a gradual impression of meaning, one can still be left asking, what do we really mean by the fabric of the universe? This is a profound question that has, in one form or another, been the subject of debate for hundreds of years. Newton declared space and time to be eternal and immutable ingredients in the makeup of the cosmos, pristine structures lying beyond the bounds of question and explanation. As he wrote in the Principia, absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Absolute, true, and mathematical time of itself, and from its own nature, flows equably without relation to anything external. Gottfried Leibniz and others vociferously disagreed, claiming that space and time are merely bookkeeping devices for conveniently summarizing relationships between objects and events within the universe. The location of an object in space and in time has meaning only in comparison with another. Space and time are the vocabulary of these relations, but nothing more. Although Newton's view, supported by his experimentally successful three laws of motion, held sway for more than 200 years, Leibniz's conception, further developed by the Austrian physicist Ernst Mach, is much closer to our current picture. As we have seen, Einstein's special and general theories of relativity firmly did away with the concept of an absolute and universal notion of space and time. But we can still ask whether the geometrical model of space-time that plays such a pivotal role in general relativity and in string theory is solely a convenient shorthand for the spatial and temporal relations between various locations, or whether we should view ourselves as truly being embedded in something when we refer to our immersion within the space-time fabric. Although we are heading into speculative territory, string theory does suggest an answer to this question. The graviton, the smallest bundle of gravitational force, is one particular pattern of string vibration. And just as an electromagnetic field such as visible light is composed of an enormous number of photons, a gravitational field is composed of an enormous number of gravitons. That is, an enormous number of strings executing the graviton vibrational pattern. Gravitational fields, in turn, are encoded in the warping of the space-time fabric, and hence we are led to identify the fabric of space-time itself with a colossal number of strings all undergoing the same, orderly, graviton pattern of vibration. In the language of the field, such an enormous organized array of similarly vibrating strings is known as a coherent state of strings. It's a rather poetic image, the strings of string theory as the threads of the space-time fabric. But we should note that its rigorous meaning has yet to be worked out completely. Nevertheless, describing the space-time fabric in this string-stitched form does lead us to contemplate the following question. An ordinary piece of fabric is the end product of someone having carefully woven together individual threads, the raw material of common textiles. Similarly, we can ask ourselves whether there is a raw precursor to the fabric of space-time, a configuration of the strings of the cosmic fabric in which they have not yet coalesced into the organized form that we recognize as space-time. Notice that it is somewhat inaccurate to picture this state as a jumbled mass of individual vibrating strings that have yet to stitch themselves together into an ordered whole, because, in our usual way of thinking, this presupposes a notion of both space and time, the space in which a string vibrates and the progression of time that allows us to follow its changes in shape from one moment to the next. But, in the raw state, before the strings that make up the cosmic fabric engage in the orderly, coherent vibrational dance we are discussing, there's no realization of space or time. Even our language is too coarse to handle these ideas, for, in fact, there's even no notion of before. In a sense, it's as if individual strings are shards of space and time, and only when they appropriately undergo sympathetic vibrations do the conventional notions of space and time emerge. Imagining such a structureless, primal state of existence, one in which there is no notion of space or time as we know it, pushes most people's powers of comprehension to their limit. It certainly pushes mine. Like the Stephen Wright one-liner about the photographer who is obsessed with getting a close-up shot of the horizon, we run up against a clash of paradigms when we try to envision a universe that is, but that somehow does not invoke the concepts of space or time. Nevertheless, it is likely that we will need to come to terms with such ideas and understand their implementation before we can fully assess string theory. The reason is that our present formulation of string theory presupposes the existence of space and time within which strings and the other ingredients found in M theory move about and vibrate. This allows us to deduce the physical properties of string theory in a universe with one time dimension, a certain number of extended space dimensions, usually taken to be 3, and additional dimensions that are curled up into one of the shapes allowed by the equations of the theory, but this is somewhat like assessing an artist's creative talent by requiring that she work from a paint-by-number kit. She will undoubtedly add a personal flair here or there, but by so tightly constraining the format of her work, we are blinding ourselves to all but a slender view of her abilities. Similarly, since the triumph of string theory is its natural incorporation of quantum mechanics and gravity, and since gravity is bound up with the form of space and time, we should not constrain the theory by forcing it to operate within an already existing space-time framework. Rather, just as we should allow our artist to work from a blank canvas, we should allow string theory to create its own space-time arena by starting in a spaceless and timeless configuration. The hope is that from this blank slate starting point, possibly in an era that existed before the Big Bang or the pre-Big Bang, if we can use temporal terms for lack of any other linguistic framework, the theory will describe a universe that evolves to a form in which a background of coherent string vibrations emerges, yielding the conventional notions of space and time. Such a framework, if realized, would show that space, time, and by association dimension are not essential defining elements of the universe. Rather, they are convenient notions that emerge from a more basic, atavistic, and primary state. Already, cutting-edge research on aspects of M theory, spearheaded by Stephen Schenker, Edward Witten, Tom Banks, Willy Fischler, Leonard Susskind, and others too numerous to name, has shown that something known as a zero brane, possibly the most fundamental ingredient in imami theory, an object that behaves somewhat like a point particle at large distances but has drastically different properties at short ones, may give us a glimpse of the spaceless and timeless realm. Their work has revealed that whereas strings show us that conventional notions of space cease to have relevance below the Planck scale, the zero branes give essentially the same conclusion, but also provide a tiny window on the new unconventional framework that takes over. Studies with these zero branes indicate that ordinary geometry is replaced by something known as non-commutative geometry, an area of mathematics developed in large part by the French mathematician Alain Connes. In this geometrical framework, the conventional notions of space and of distance between points melt away, leaving us in a vastly different conceptual landscape. Nevertheless, as we focus our attention on scales larger than the Planck length, physicists have shown that our conventional notion of space does reemerge. It is likely that the framework of non-commutative geometry is still some significant steps away from the blank slate state anticipated above, but it does give us a hint of what the more complete framework for incorporating space and time may involve. Finding the correct mathematical apparatus for formulating string theory without recourse to a pre-existing notion of space and time is one of the most important issues facing string theorists. An understanding of how space and time emerge would take us a huge step closer to answering the crucial question of which geometrical form actually does emerge. Will string theory lead to a reformulation of quantum mechanics? The universe is governed by the principles of quantum mechanics to fantastic accuracy. Even so, in formulating theories over the past half-century, physicists have followed a strategy that, structurally speaking, places quantum mechanics in a somewhat secondary position. In devising theories, physicists often start by working in a purely classical language that ignores quantum probabilities, wave functions, and so forth. A language that would be perfectly intelligible to physicists in the age of Maxwell, and even in the age of Newton, and then subsequently overlaying quantum concepts upon the classical framework. This approach is not particularly surprising, since it directly mirrors our experiences. At first blush, the universe appears to be governed by laws rooted in classical concepts such as a particle having a definite position and a definite velocity at any given moment in time. It is only after detailed microscopic scrutiny that we realize that we must modify such familiar classical ideas. Our process of discovery has gone from a classical framework to one that is modified by quantum revelations, and this progression is echoed in the way that physicists, to this day, go about constructing their theories. This is certainly the case with string theory. The mathematical formalism describing string theory begins with equations that describe the motion of a tiny, infinitely thin piece of classical thread. Equations that, to a large extent, Newton could have written down some 300 years ago. These equations are then quantized. That is, in a systematic manner developed by physicists over the course of more than 50 years, the classical equations are converted into a quantum mechanical framework in which probabilities, uncertainty, quantum jitters, and so on are directly incorporated. In fact, in Chapter 12, we have seen this procedure in action. The loop processes incorporate quantum concepts, in this case, the momentary quantum mechanical creation of virtual string pairs, with the number of loops determining the precision with which quantum mechanical effects are accounted for. The strategy of beginning with a theoretical description that is classical and then subsequently including the features of quantum mechanics has been extremely fruitful for many years. It underlies, for example, the standard model of particle physics. But it is possible, and there is growing evidence that it is likely, that this method is too conservative for dealing with theories that are as far-reaching as string theory and M-theory. The reason is that once we realize that the universe is governed by quantum mechanical principles, our theories really should be quantum mechanical from the start. We have successfully gotten away with starting from a classical perspective until now, because we have not been probing the universe at a deep enough level for this coarse approach to mislead us. But with the depth of string/M theory, we may well have come to the end of the line for this battle-tested strategy. We can find specific evidence for this by reconsidering some of the insights emerging from the second superstring revolution. As we discussed in Chapter 12, the dualities underlying the unity of the 5 string theories show us that physical processes that occur in any one-string formulation can be reinterpreted in the dual language of any of the others. This rephrasing will at first appear to have little to do with the original description, but in fact this is simply the power of duality at work. Through duality, one physical process can be described in a number of vastly different ways. These results are both subtle and remarkable, but we have not yet mentioned what may well be their most important feature. The duality translations often take a process, described in one of the 5 string theories, that is strongly dependent on quantum mechanics. For example, a process involving string interactions that would not happen if the world were governed by classical, as opposed to quantum physics, and reformulated as a process that is weakly dependent on quantum mechanics from the perspective of one of the other string theories, for example, a process whose detailed numerical properties are influenced by quantum considerations, but whose qualitative form is similar to what it would be in a purely classical world. This means that quantum mechanics is thoroughly intertwined within the duality symmetries underlying string/M theory. They are inherently quantum mechanical symmetries, since one of the dual descriptions is strongly influenced by quantum considerations. This indicates forcefully that the complete formulation of string-M theory, a formulation that fundamentally incorporates the newfound duality symmetries, cannot begin classically and then undergo quantization in the traditional mold. A classical starting point will necessarily omit the duality symmetries, since they hold true only when quantum mechanics is taken into account. Rather, it appears that the complete formulation of string/M theory must break the traditional mold and spring into existence as a full-fledged quantum mechanical theory. Currently, no one knows how to do this, but many string theorists foresee a reformulation of how quantum principles are incorporated into our theoretical description of the universe as the next major upheaval in our understanding. For example, as Kumrun Vafa has said, I think that a reformulation of quantum mechanics which will resolve many of its puzzles is just around the corner. I think many share the view that the recently uncovered dualities point toward a new, more geometrical framework for quantum mechanics, in which space, time, and quantum properties will be inseparably joined together. And according to Edward Witten, I believe the logical status of quantum mechanics is going to change in a manner that is similar to the way that the logical status of gravity changed when Einstein discovered the equivalence principle. This process is far from complete with quantum mechanics, but I think that people will one day look back on our epoch as the period when it began. With guarded optimism, we can envision that a reframing of the principles of quantum mechanics within string theory may yield a more powerful formalism that is capable of giving us an answer to the question of how the universe began and why there are such things as space and time, a formalism that will take us one step closer to answering Leibniz's question of why there is something rather than nothing. Can string theory be experimentally tested? Among the many features of string theory that we have discussed in the preceding chapters, the following three are perhaps the most important ones to keep firmly in mind. First, gravity and quantum mechanics are part and parcel of how the universe works, and therefore any purported unified theory must incorporate both. String theory accomplishes this. Second, studies by physicists over the past century have revealed that there are other key ideas, many of which have been experimentally confirmed, that appear central to our understanding of the universe. These include the concepts of spin, the family structure of matter particles, messenger particles, gauge symmetry, the equivalence principle, symmetry breaking, and supersymmetry, to name a few. All of these concepts emerge naturally from string theory. Third, unlike more conventional theories such as the Standard Model, which has 19 free parameters that can be adjusted to ensure agreement with experimental measurements, string theory has no adjustable parameters. In principle, its implications should be thoroughly definitive. They should provide an unambiguous test of whether the theory is right or wrong. The road from this in-principle ratiocination to an in-practice fact is encumbered by many hurdles. In Chapter 9, we described some of the technical obstacles, such as determining the form of the extra dimensions, that currently stand in our way. In Chapters 12 and 13, we placed these and other obstacles in the broader context of our need for an exact understanding of string theory, which, as we have seen, naturally leads us to the consideration of M-theory. No doubt, achieving a full understanding of string M-theory will require a great deal of hard work and an equal amount of ingenuity. At every step of the way, string theorists have sought and will continue to seek experimentally observable consequences of the theory. We must not lose sight of the long-shot possibilities for finding evidence of string theory discussed in Chapter 9. Furthermore, as our understanding deepens, there will, no doubt, be other rare processes or features of string theory that will suggest yet other indirect experimental signatures. But most notably, the confirmation of supersymmetry, through the discovery of superpartner particles as discussed in Chapter 9, would be a major milestone for string theory. We recall that supersymmetry was discovered in the course of theoretical investigations of string theory, and that it is a central part of the theory. Its experimental confirmation would be a compelling, albeit circumstantial, piece of evidence for strings. Moreover, finding the superpartner particles would provide a welcome challenge, since the discovery of supersymmetry would do far more than merely answer the yes-no question of its relevance to our world. The masses and charges of the superpartner particles would reveal the detailed way in which supersymmetry is incorporated into the laws of nature. String theorists would then face the challenge of seeing whether this implementation can be fully realized or explained by string theory. Of course, we can be even more optimistic and hope that within the next decade, before the Large Hadron Collider in Geneva comes online, the understanding of string theory will have progressed sufficiently for detailed predictions about the superpartners to be made prior to their hoped-for discovery. Confirmation of such predictions would be a monumental moment in the history of science. Are there limits to explanation? Explaining everything, even in the circumscribed sense of understanding all aspects of the forces and the elementary constituents of the universe, is one of the greatest challenges science has ever faced. And for the first time, superstring theory gives us a framework that appears to have sufficient depth to meet the challenge. But will we ever realize the promise of the theory fully and, for example, calculate the masses of the quarks or the strength of the electromagnetic force, numbers whose precise values dictate so much about the universe? As in the previous sections, we will have to surmount numerous theoretical hurdles on the way to these goals. Currently, the most prominent is achieving a full, non-perturbative formulation of string/M theory. But is it possible that even if we had an exact understanding of string/M theory, framed within a new and far more transparent formulation of quantum mechanics, we could still fail in our quest to calculate particle masses and force strength? Is it possible that we would still have to resort to experimental measurements rather than theoretical calculations for their values? And, moreover, might it be that this failing does not mean that we need to look for an even deeper theory, but simply reflects that there is no explanation for these observed properties of reality? One immediate answer to all these questions is yes. As Einstein said some time ago, the most incomprehensible thing about the universe is that it is comprehensible. The astonishment at our ability to understand the universe at all is easily lost sight of in an age of rapid and impressive progress. However, maybe there is a limit to comprehensibility. Maybe we have to accept that after reaching the deepest possible level of understanding science can offer, there will nevertheless be aspects of the universe that remain unexplained. Maybe we will have to accept that certain features of the universe are the way they are because of happenstance, accident, or divine choice. The success of the scientific method in the past has encouraged us to think that with enough time and effort we can unravel nature's mysteries. But hitting the absolute limit of scientific explanation, not a technological obstacle or the current but progressing edge of human understanding, would be a singular event, one for which past experience could not prepare us. Although of great relevance to our quest for the ultimate theory, this is an issue we cannot yet resolve. Indeed, the possibility that there are limits to scientific explanation, in the broad way we have stated it, is an issue that may never be resolved. We have seen, for instance, that even the speculative notion of the multiverse, which at first sight appears to present a definite limit to scientific explanation, can be dealt with by dreaming up equally speculative theories that, at least in principle, can restore predictive power. One highlight emerging from these considerations is the role of cosmology in determining the implications of an ultimate theory. As we have discussed, superstring cosmology is a young field, even by the youthful standards set by string theory itself. It will undoubtedly be an area of primary research focus for years to come, and it is likely to be one of the major growth areas of the field. As we continue to gain new insight into the properties of string/M theory, our ability to assess the cosmological implications of this rich attempt at a unified theory will become ever sharper. It is possible, of course, that such studies may one day convince us that, indeed, there is a limit to scientific explanation. But it is also possible, to the contrary, that they will usher in a new era, an era in which we can declare that a fundamental explanation of the universe has finally been found, reaching for the stars. Although we are technologically bound to the Earth and its immediate neighbors in the solar system, through the power of thought and experiment we have probed the far reaches of both inner and outer space. During the last 100 years in particular, the collective effort of numerous physicists has revealed some of nature's best-kept secrets. And once revealed, these explanatory gems have opened vistas on a world we thought we knew, but whose splendor we had not even come close to imagining. One measure of the depth of a physical theory is the extent to which it poses serious challenges to aspects of our worldview that had previously seemed immutable. By this measure, quantum mechanics and the theories of relativity are deep beyond anyone's wildest expectations. Wave functions, probabilities, quantum tunneling, the ceaseless roiling energy fluctuations of the vacuum, the smearing together of space and time, the relative nature of simultaneity, the warping of the spacetime fabric, black holes, the Big Bang. Who could have guessed that the intuitive, mechanical, clockwork Newtonian perspective would turn out to be so thoroughly parochial, that there was a whole new, mind-boggling world lying just beneath the surface of things as they are ordinarily experienced? But even these paradigm-shaking discoveries are only part of a larger, all-encompassing story. With solid faith that laws of the large and the small should fit together into a coherent whole, physicists are relentlessly hunting down the elusive, unified theory. The search is not over, but through superstring theory and its evolution into M-theory, a cogent framework for merging quantum mechanics, general relativity, and the strong, weak, and electromagnetic forces has finally emerged. And the challenges these developments pose to our previous way of seeing the world are monumental. Loops of strings and oscillating globules, uniting all of creation into vibrational patterns that are meticulously executed in a universe with numerous hidden dimensions, capable of undergoing extreme contortions in which their spatial fabric tears apart and then repairs itself. Who could have guessed that the merging of gravity and quantum mechanics into a unified theory of all matter and all forces would yield such a revolution in our understanding of how the universe works? No doubt, there are even grander surprises in store for us as we continue to seek a full and calculationally tractable understanding of superstring theory. Already, through studies in M-theory, we have seen glimpses of a strange new domain of the universe lurking beneath the Planck length, possibly one in which there is no notion of time or space. At the opposite extreme, we have also seen that our universe may merely be one of the innumerable frothing bubbles on the surface of a vast and turbulent cosmic ocean called the multiverse. These ideas are at the current edge of speculation, but they may presage the next leap in our understanding of the universe. As we fix our sight on the future and anticipate all the wonders yet in store for us, we should also reflect back and marvel at the journey we have taken so far. The search for the fundamental laws of the universe is a distinctly human drama, one that has stretched the mind and enriched the spirit. Einstein's vivid description of his own quest to understand gravity, the years of anxious searching in the dark, with their intense longing, their alternations of confidence and exhaustion, and final emergence into the light, encompasses surely the whole human struggle. We are all, each in our own way, seekers of the truth, and we each long for an answer to why we are here. As we collectively scale the mountain of explanation, each generation stands firmly on the shoulders of the previous, bravely reaching for the peak. Whether any of our descendants will ever take in the view from the summit and gaze out on the vast and elegant universe with a perspective of infinite clarity, we cannot predict. But as each generation climbs a little higher, we realize Jacob Bronowski's pronouncement that, in every age there is a turning point, a new way of seeing and asserting the coherence of the world. And as our generation marvels at our new view of the universe, our new way of asserting the world's coherence, we are fulfilling our part, contributing our rung to the human ladder reaching for the stars. If you enjoyed this audiobook, don't forget to follow for more stories and knowledge coming your way.